like president or someone high up in the company was trapped in I think Vancouver, right? And I had forgotten, and I was like, oh yeah, she's like, we have not forgotten.
Sorry, could the slides when they're active, could they be maximized as opposed to like the video?
Yeah, they can. The point of this is so we all can see the chat and stuff in the room too. They wanted that, but yeah, we can set it up to where it'd be full screen. People will be able to see the chat.
Yeah, so I think.
You want the full screen?
Okay, thank you.
Still is. So they were double check. So I re-uploaded.
I think okay. We're right line.
Oh, I'm sure.
Yeah, I think there's a sort of like a natural thinking about you know, we're joking, but you're coming. Yeah, you're very I saw that too, yes. Virginia
Someone else to awkward questions.
Virginia Tech. I saw that too.
I'm not certain.
Have you been to that?
For years, I've been taking advantage of the fact that the guy next to me works on Interstate Road, Jonathan Cameron. And with the publication there, I never figured out with different people. Neither of us has ever been to point. I'm quite honest. It's personality. Could be too hot.
The chat from last year?
Yes.
I have not been on chat. I've multiple comments on there.
Who's going to heckle from online? Does anyone know if you can hear that part of questions? Because that was the problem. Getting around the stand. Hopefully it's Steve's. Like bingo, how many times I mean, it would for a whole lot. We made it yeah, we can run a lot. We probably shouldn't push that too. Because to be honest, last time we got thrown out.
Oh, finding out your relatives.
We should try and get the comment back on time. You've got to keep us on time. No letting us run on like
There's a 10-minute offset. Because essentially.
All right. All right. All right, 2:31, so might as well get started. Welcome everyone to the CXL micro conference. Very glad to see you all. Thank you for our sponsors. And I'm also supposed to say that we are under a anti-harassment policy, so please everyone behave. And yeah, we have till 6 o'clock this evening, and the way it's structured is kind of a bit how we do the online upstream meetings with a state of the art of QEMU first, and then we'll have presentations upon some of the different things driver related that are being worked on currently that need proper discussion. And gradually go on to some memory management topics towards the end. The idea is to discuss, participate, and when everyone has a question, please stand up so that you can be seen. And yeah, let's go ahead and start. First up, QEMU.
Anyway, so hopefully good enough. Okay, so welcome back to what is effectively the second presentation on the QEMU side of things. Last time, we spent some time introducing why we were doing emulation of CXL in QEMU. This time, we're going to jump straight over that bit and move on to kind of a bunch of stuff on what's new. So Fan is going to be co-presenting on the basis that he's done a lot of work on the DCD emulation, so he's going to handle that part when we get onto it. But first of all, yeah, a quick agenda. So we're going to talk a little bit about what landed since last year, some stuff on major topics in flight, and the key bit is discussion over what's next. As I say here, jump in at any point with questions. Just feel free to stick your hand up or stand up, and you'll get hit on the head by a thrown mic, and hopefully can raise your question. I put a proviso at the bottom here. No, we're only going to talk about stuff in published specifications. I'm usually the militant one on this, so I may just say nope, can't talk about that. The very nature of CXL is it's moving fairly quickly, and there's lots of new and exciting stuff coming. So some very small text. Sorry about that. Anyway, yeah, so before LPC last year, we did sort of basic enablement. Since then, a number of things have landed upstream in the last year. So thanks to those various people who worked on these. I'm not going to call out names because I always forget people. So we've got volatile support, multiple HDM decoders, CDAT, RAS error injection, poison injection, all that stuff. Under review, various other things like dynamic capacity devices. The things with stars, hopefully you can see the stars, are the things that we're going to go into in a little bit more depth. So save your questions on those for now. Yep, things like CCI, reworking to support fabric management. That's been a big topic I've been working on recently. Scanning media stuff. We have a bunch of things sat in the staging tree that we operate for QEMU that have not gone upstream for various reasons. Quite happy to talk about those. Let's address that a little bit later. And we have a few other things that have been posted for discussion on the mailing list, but no real intent yet to upstream them. And in fact, the next talk is going to involve some type 2 stuff from Ira. I don't know if he's talking about the QEMU bit, but hopefully. So, handing over to you.
Oh, hello everyone. My name is Fanny. I'm from Samsung. Today I'll give a brief update about the dynamic capacity device emulation in QEMU. So I'll start with a brief recap about the dynamic capacity device. So before the introduction of a dynamic capacity device, if we want to add or release some memory capacities for CXL memory, actually it can be very disruptive because the host need to be reprogrammed to cover the range of the device changed. And also like all outstanding traffic to the device need to be quiesced. And also most of the time the system reset is required. So with DCD devices, it's much easier and convenient to do like allocation or deallocation memory capacities without the need to reprogram the HDM decoders. So the basic idea is that present the maximum capacity of the device to the host, and then the host can program the HDM decoders to cover the whole DPA range. And the device provide a set of commands to control the real like allocation and deallocation of the ranges that can be accessed by the host. So this is the basic like unit for allocation and deallocation. It's called dynamic capacity extents. Basically, it's a continuous range of blocks. So what we have now for dynamic capacity device emulation in QEMU. So currently, it's quite simple. We augmenting the type 3 memory devices with dynamic capacity. So before that, we have like a volatile and non-volatile static capacity for type 3 devices. Now we had a third one called dynamic capacity. It's backed with 1 to 8 configurable dynamic capacity regions. And also in the device, we maintain a extend list representing the DPA ranges that can be used by the host. And also we support the basic read-write access to the dynamic region, and also provide some mechanism to validation to make sure actually the address range is backed by valid like extents. So to control and use the device, we also implement some mailbox command. Like for example, we can use like the get dynamic capacity configuration command from the host to retrieve the dynamic capacity region informations like start address of the region, the length of the region, and so on. And the host can also use like a get dynamic capacity extend list to retrieve the DPA ranges that it can use at this moment. Since this extended list is like can dynamically change when we add more extents or remove some extents from the host. So whenever we want to get the latest the DPA ranges we want to access, we can use this command to do that. And the add dynamic capacity response command is used to respond to a dynamic capacity add event in the event log. So whenever we see dynamic capacity add event in the event log, and the host can, after the host like process the event, and it can send the add dynamic capacity response to the device to show in like whether it will accept the extent or just reject it. And whenever the host want to release the dynamic capacity extent, it will send this release dynamic capacity command. This can be a response to the dynamic capacity release like event in the event log, or just because the host don't want to use the extent anymore. So based on the specification, like the FM is the main component to issue the add dynamic capacity extend or release like a dynamic extend. But at this moment, we don't have a fabric manager in QEMU, so we use like a QMP interface to simulate it, so we can use this interface to send like a dynamic capacity add or release command to the to the device, and the device will add the extents in the event log. The host can retrieve from there and process accordingly. So with the functionalities mentioned above, we can make some very simple tests and also support the kernel side code development for dynamic capacity support. But we are still missing something important. I think that's really something that makes dynamic capacity very meaningful and useful. For example, currently we only add dynamic capacity to the simple type 3 mem device, but for more complicated devices like multi-headed devices and FAM or GFD, these devices is supposed to be the main scenarios will use dynamic capacity device, but we don't have support yet. And also for the DC regions, currently we hard-coded as non-volatile, but this is easy to fix in the future if we want to support volatile regions as well. And also at this moment, we do not support shared extents. That means each extent is only used by one host. So any tag related to sharing actually is there, but it's not used or tested at all. And also the extend list, the generation number is there, but it's not used. That one should be easy to fix later if we have the need there. And also all the add or release capacity actually is based on the extend list. So low tag based operations there. For example, for the release command, actually based on the specification, we can release based on the tag. But currently we don't have that support in there since tag is not used actively now. And also all the dynamic management command set from the FM side is not there because FM is not there. So we also noticed some issues about the current CXL spec 3.0 for dynamic capacity support. For example, the first issue we have noticed actually is that the spec mentioned that FM is the main component to initialize to add multiple extend in one request. From the definition of the request payload, we see there is an extend list there. But the text also mentioned that each request actually may at most result in one record in the event log. But based on the dynamic capacity event record, it can hold only one one extend there. So if we want to add or release multiple extend in one request, actually we cannot do it in one by inserting one record in the event log. So that's something supposed to be fixed in future versions of the specification. Another thing, similar thing here is that when the host responds to a dynamic capacity add event, the text also mentioned that the host will send exactly one response there, but the response payload also includes a extend list. So if it's a response to one record, so that means the extend list can hold at most one record there, just a one extend or low extend at all. This is based on current 3.0 specification, and so this subset means mentioned in the text extends accepted by the host can be a subset of what have been offered by the device actually can only be 0 or 1. So this is something need to be fixed in future specifications. There are some other things, but I haven't mentioned in this talk yet. Okay, that's all for.
Can you force release from QEMU, like the QMP interface, or do you have that support yet?
That command is not added yet, but it should be easy because like you only need to change the event type.
Okay.
Yeah.
And then IRA is covering DCD on the kernel side, right? Okay.
Yeah.
I'll save that for later.
I had a general question. What was the motivation for non-volatile support by default? Like,
I think that's just because like even for the static capacity, we first support like non-volatile, and then on the kernel side, like when we process like non-volatile, volatile seems to be more complicated because it needs auto like discovery, right? There, so when I implemented, actually, I just want to make it simple and usable, can be tested easily. But there's not saying like we cannot support like volatile. Yeah.
Did the patches from Gregory ever go up for volatile support? No. Did the patch because there should be nothing fundamentally different about supporting volatile versus non-volatile. I think this is the ghost of PMEM is why it's the QEMU support started with non-volatile, but there's nothing.
Yeah.
The reality is it doesn't make any difference. I had to pick one value for the flag.
Yeah.
The volatile support would have been landing roughly in parallel with your work.
Yeah.
So while it is upstream, it probably wasn't when you started.
Okay.
So, fair enough.
Yeah.
Yeah, there'll be plenty of time for more questions about DCD at the end, hopefully. How are we doing? Okay. Next up, there's a lot of material in this bit, so feel free to ask questions and dive a little bit deeper. But the topic here is fabric management. So debated for a while whether it made sense to emulate this in QEMU, because it isn't something that is directly visible to the host, but things like dynamic capacity are very strong justifications for why we do need at least some of the fabric management, as Fanny mentioned a moment ago. I snuck a star in on his slides when he said there wasn't any FM support, because there is one command in one of the staging trees. It's completely useless, but it was just showing how it would work. You can add capacity, but you can't remove it. So it's the same reason for emulation, basically, as we had for doing the QEMU emulation in the first place, which is as a test bench for, in this case, fabric managers, providing us something where we can tweak things, get an idea of how it all fits together. We are very much in the early stages for open source fabric managers. There's some test code. I'm not sure if there's anything yet out there corresponding to a full stack. But if anyone does have one and wants to talk about it, let me know, because I'd love to know what to test with. The other classic here is CXL standards prove out. I think the exercise of doing the original QEMU emulation and indeed all of the kernel work is showing that not everything can be considered in a spec that runs quite so far ahead of where hardware is. So it's very useful from that side of things. Another key thing here is if we are driving some of these complex devices, so some of the switches and the configurability of those, or indeed dynamic capacity, it's really handy to have a standard interface to poke it with. And adding the fabric management gives us that option. And we'll come on to exactly how that comes together. I have added a note here that we're not talking about CXL3 fabrics in this case. This is the simpler version of fabric management where it all looks a bit like a PCI topology. So there'll be a lot of slides here with a lot of lines on them, but hopefully I'll skip through what we're covering. So there are all sorts of different communication channels. Hey, Dan.
Well, so kind of the fundamental question, and it's good to ask, I think, in this kind of context, is like we upstreamed the QEMU support for CXL because we need like pre-hardware, but we had a production use case for the kernel code, and the devices are coming. You might have seen my comments on the switch CCI stuff. Like we don't do we, or like the upstream consumer for switch CCI and the kernel side is not as clear to me. Like, what are we building? Like, basically, I'm not super confident about just landing kernel code just for testing.
Yeah. Well, I think the key thing is the blob on the left here is I agree it's not a normal host kernel. I think we will see BMCs
making use of this in the same sense that they make use of some of the MCTP stack that frankly the kernel supports and doesn't get used from Linux.
So should I be reviewing these patches in the context of when somebody else from a BMC land comes along and says, hey, we want to build fabric manager interfaces, like this is the ABI that we are recommending for you to use?
Well, I think the last thing we want to do is to end up with a Linux kernel running on a BMC stack that bears no resemblance to the main kernel stack where there are shared components. And particularly for the switch CCI, we've also got the PCI mailbox thing, which is MMPT, which is kicking around, which is going to see some use from hosts because it's much more heavily used for things like firmware update.
Who's gonna work on the blob of the BMC part, right? Like, so I see the pieces there for the switch CCI, but I think it would make it very clear for people if you're like, okay, this is exposing it over TCP to another host, right? And then you talk to the FM, like, so the pieces are there, right? Like it's almost there, but it's not real, right? And so
there was a lot of discussion and a lot of diagrams drawn on the many, many forms of Fabric Manager that you can evolve. And to be fair, this one is focusing on the very simplest, which is simply a memory appliance with, and in this case, the BMC is just the controller of that memory appliance. So commands coming into that will come over something else. They won't be over FM API. They'll be Redfish or one of the DMTF standards. So, some of that stuff's still being defined.
Okay. So it's still weird with QEMU because like the current switch is owned by a host, single host, right? So there's no real mechanism to discover ports that are coming from somewhere else, right? Like it doesn't make complete sense, right? Like from a QEMU perspective, right? What do you think about that?
Agreed. You're absolutely right. There have been discussions on how to broaden to multi-host QEMU for precisely that reason, so that you'll be able to run a number of hosts.
Who's working on this? Is this in public domain that people are talking about this?
There's been a few discussions in feedback on some of the patches about it.
Okay.
And I've had a number of other people reach out and say, oh, can we do this slightly crazy thing? Because they are very much interested in working on the large scale fabric managers. And if you can poke some data through.
Okay.
Because there are, I mean, people have looked at emulating just that without the hosts involved as well. And the problem is you never prove your full use case. You prove a little emulator of just the fabric wiring.
More thing, and I'll let you get on with it. So are these switch CCIs going to be hidden? Like, imagine we have QEMU, BMC running. BMC is going. Are you expecting BMC is discovering these switch CCIs itself and they're invisible to the host, or in that kind of environment?
We'll get there.
Okay.
Absolutely, the expectation. There's nothing in the QEMU configuration that says the switch CCI needs to be on the same topology as the host is. I mean, the reality, we only have one topology at the moment, so it would just end up on a different root port. But you can certainly do that sort of configuration. We'll come on to a little bit more on combining the BMC and the host for testing purposes. Anyway, this slide is just meant to say there's some in-band stuff. That was kind of it. And we will build up. Another thing that's crucial for fabric management is MCTP over various transports. There are a lot of them drawn on here. So you can see there's a whole bunch of wires going to effectively every component. This is looking at the outer band type signaling. So this would be something like I2C, I3C, or I mean, it could be Ethernet, could be any number of different things. MCTP is carried over almost anything. This includes stuff like the multi-headed device pool CCIs. There are other paths to get to those, which we'll come back to. Basically you wire everything to everywhere. And so we need a path to emulate that. Moving on to the next bit. Now, you notice that there's no new stuff in the list of things we can do with this, but this is just introducing the fact that MCTP can also be carried over vendor-defined messages on PCI, which becomes relevant in the next slide. Yeah, feel free to look at these later. There's a lot of lines. Okay, so the key thing here is that this ability to carry them over PCI VDM enables the tunneling concept. So you can go into, say, a switch, and then you can tunnel down through the downstream ports of that switch to the individual devices below it and configure all of them. You can also tunnel out from where you first hit. Once you go the downstream device where you hit something that's owned by the fabric manager, you can tunnel out to the individual devices exposed to a host and do things like set the label storage area or pre-configure stuff. You can actually send PCI writes and reads as well. So you can configure anything. Yep. I can't even read the slide. Yes, that's just saying what I said. Okay. Yes. So this is the question Dan was asking about, which is how are we emulating the switch CCI or indeed the rest of this stuff? Now, under normal circumstances, this would be a different host. That's not something that's easy to do in QEMU today. There are out-of-tree solutions for this. We're aware of a number of companies who have such solutions. If anyone wants to speak up. 5 minutes. I thought you were saying you wanted to speak up. Darn it. Yeah, they do exist. So there are multi-host QEMU setups that are useful for exactly this BMC type emulation. But for now, and also useful for testing purposes, what we actually do is we sweep everything in the BMC round and push it on to the host. And in fact, we actually combine multiple hosts as well. This allows us to exercise all of the various paths of things going away, reappearing, all of the DCD flows, all of that stuff can then be poked from a single host, which makes testing a lot simpler, hopefully. Although, as I say, we only have one command at the moment for DCD. Okay, so skipping on, and I don't propose to talk about anything on this slide. This is here as a prompt list in case anyone doesn't have any questions. But the aim at this point is to address what people are interested in seeing, what they're not seeing at the moment in the CXL emulation.
So there's a question
Mhm.
online. Lee's asking, is there a plan to enable KVM and CXL emulation with the node problem? Yes. Well,
as long as you don't like instructions. I mean, without instructions, it works perfectly. No, you can use it. Data's fine. Execute. Okay, so the fundamental problem here is that for CXL, the granularity of interleave, which we've emulated for a long time, is much finer than page level. Now, in order to do any of the stuff that's done with KVM, etc., you tend to do it in page tables. So at best, you've got 4K. Combining the two is a bit of a problem. Actually, even in TCG, we had a problem for a while because it didn't handle x86 instructions that went across a page boundary. But the reality is the way we're handling it at the moment is every single read or write has to go through the ultimate slow path in TCG, which means there's no caching of instruction translations, any of that stuff. So it's very slow. And also with KVM, in order to make that work, you would have to add emulation of pretty much every instruction to the kernel. And that's just not going to fly. Now, we have had discussions about how to do this. We can put caching layers in between. But the fundamental question is, do we actually care? As a general rule, the QEMU emulation is not there for performance cases. We do have a problem at the moment, which is that it's so bad that it tends to stall completely if you're running any programs out of this memory, which does make certain types of testing a little challenging. Leads to some not helpful bug reports along the lines of it don't work, which we're fully aware of. So it's absolutely something that we can look to address, but it's a big and complex bit of work. And it's not clear if it's worth doing. Yeah, I stuck it down here as performance optimization, but yeah, I guess KVM is a really big performance optimization. So it was a good question. Any other questions at this point? Or jump on anything on there. Oh, we've got someone at the back. Throw him a mic.
It says ARM support. Could use some help at the bottom. Can you go into a little detail on that for me?
Oh, yes.
Excellent. Thank you.
So one of the things on the ARM support is we're trying to add it to ARMvert in QEMU. Now, the problem with ARMvert is it has a fairly strong rule that it must have device tree support. There are one or two things that have slipped through when maintainer didn't notice. So one of those is the PXB stuff, the PCI expander bridges. Now, those are used by, well, they're used for a bunch of reasons around NUMA topologies and things normally, but the CXL device is a descendant of one of those. And the problem with those is they have an enumeration problem, which is that they're actually enumerated by EDK2. And if you're in, so you go through a double firmware build thing. So you build enough information to pass to the BIOS. The BIOS then enumerates the entire PCI topology and fills in the gaps for all the PXBs. And then you go back into QEMU, which rebuilds all the tables before providing them to the distro or whatever's running on top. In device tree, there's no such path. So the discussion there is, what on earth can we do about enumerating these? We could enumerate them in the kernel, but is the kernel going to take a bunch of nasty support for what is basically a QEMU hack? We could do static enumeration. I gave a talk at Lenora Connect on this earlier in the year and got some good feedback from the maintainers there, but we haven't solved it.
I mean, I feel like the idea that and QEMU is going to need to get arbitrary device trees passed into it. Like if you're running an ARM kernel under QEMU, intrinsically you have to describe the whole platform you're running on. So to me, the idea that
I say, got to throw it back.
We're done.
Just make him walk. We're done. Out of time. Anyway, carry on afterwards. I can talk for that one for many hours.
I hope Ira is online. And
Yes, I am trying to get my camera
All
going
right.
here. Can you all see me or? Okay, well, I guess we'll do that.
We can see you now.
Yeah? Okay. Are my slides?
Nope. Well, David Law's looking passive.
sorry about that.
So I'll just kind of get started here since I'm remote. Sorry that I couldn't be there. So I'm going to talk a little bit about type 2. When I proposed this, talk, I hoped that there would be a little bit more interest in the community going forward. And can I actually control these?
Yeah, the slides uploaded. It's just not changing.
Yeah, it did for you.
CXL ARM memory.
Is that it?
We can't hear you
I
now.
can't hear you. Yeah. Is someone moving it back and forth?
I'm sorry. I guess I muted myself. I almost left the conference. So, all right. So when I proposed this talk, I was really hoping that there would be some interest in the community as we talked on the mailing list, and unfortunately, that really hasn't materialized. So I'm just going to talk a little bit about what we're driving at towards the core, and let people get some information about if their companies are planning a type 2 device but they just can't talk about it or whatever, we can hope to have a more seamless merge into the main core. As maintainers, Dan and I have talked about this a lot, and so we're looking for, number one, general interest. Is anybody in the community looking at type 1 or type 2 devices? Basically accelerator devices, as the title of the talk was, beyond memory. So go ahead and flip to the next page, and then we'll go through type 1 and 2 current work. And then since I'm also presenting a little bit of DCD, I thought I'd just give a little bit of time back to DCD because that seems to need a lot more discussion. There's a lot more going on in the community there, a lot more moving parts and participants. So, for those who don't know, type 1 has direct access to main memory with .cache, and type 2 has both direct access. And so we're really targeting in the core type 2, which will cover effectively both of these protocols and allowing accelerators to leverage core support within the core drivers that, drivers CXL and that code. So we can kind of ignore type 1 unless somebody has a specific need for that. But those are going to be mainly driven by the drivers and the accelerator itself. So I guess flip to the next slide. So now we're going to get into really the point. So for those of you who may be interested in type 2, you might have known that Dan already posted some RFC work. Some work for type 2 devices has actually landed. There's some splitting of data structures that's in the upstream kernel that will allow the core to better support accelerators and their .mem usage to be able to create regions. But that was only the patches that we really needed to, clean up the core as it stands today, because without a good use case, we haven't tried to upstream all of that work. Dan threw the series at me, and I've recently rebased it, and I plan to post that. There is one fix that I think should actually land upstream relatively quickly, even though the fix doesn't materialize without a test driver. I still think it's appropriate to get upstream to clarify some of that data structure splitting that was done and is currently upstream. And we're focusing on a number of things. Number one is coordinating between any accelerator drivers in the core. So, what we're driving towards is, what does the core need to do to make sure that any accelerator drivers leverage the core kernel code, creating regions, managing address of space for those memories that accelerators are going to have. We don't want to see accelerators go off and try to re-implement what's currently in the CXL core. We also want to provide facilities to, check and enumerate the link capabilities and allow drivers to focus on driving their hardware, not trying to manage walking the CXL trees or switches and links and doing, that type of work. We want that to be in the core, so the patch set covers that type of support. And then any user space interaction that may need to be done. I'm still a little bit on the fence on this one, because right now the patch set is targeting accelerator drivers to create regions. I feel like, and of course this is totally up in the air, but I feel like there might be a use case for accelerator drivers to leverage the current region DAX control device support. But I think that's all going to only materialize once we actually have a device and we know what the use cases for those devices are. So that's just a gut feeling on my part at this point. And then, of course, as I'll mention in the DCD talk as well, anything that goes upstream, Dan and I have talked about this, and Dan is a very big believer in CXL test, for those of you who don't know. But I've kind of converted with my work on DCD. I've really converted over to really liking CXL test, and we feel that any features that go upstream need to have some sort of CXL test or a good reason that, say, QEMU needs to be used to test it instead or in addition. So moving on to QEMU support, I did throw a very quick accelerator device out onto the mailing list a few months back, and it was relatively easy to derive a dummy accelerator device from a .memory device. Those devices are already available, obviously. And the idea there was really just to emulate the type of support in the hardware that the core was going to check, such that the core code could be tested. At this point, we probably could do that with CXL test. So I really don't know how far we should really go with QEMU or not. It's really kind of a what's best. With some work, I implemented testing for event processing in both CXL test and QEMU, and QEMU offered a lot of interesting test cases. But strictly speaking, it wasn't required. So I'm leaning towards that with QEMU, but or I'm leaning towards that with type 2 support, is that potentially QEMU support may not be needed just to get the testing in the core that we need for the core, because most of the testing, quote unquote, for accelerators will really be based on the devices that are being developed. So, that's a place where QEMU support would be more advantageous. And I think that's up to the device vendors who are building these devices and what they'll need. So I don't really see QEMU support going too much further than what I've hacked together.
I have a question. So at OCP, I saw Intel type 2 kernel same page merging, right? Have you seen this? Okay, Dan doesn't know about this. Okay. I forgot the guy's name. I don't know. Ira, have you heard about this?
No, I have not.
Okay, there's someone at Intel working on for the FPGAs, right? And so yeah, it's not. What is the same page merging? What is it called? What is the kernel same page merging? Yeah, KVM. Yeah, they offloaded it to the FPGA. So,
okay.
Anyway, heads up. So you might want to find out who that is and what they're working on.
Right.
But yeah, I was gonna say, like, yeah, the FPGA people. Not trying to be rude, but in terms of like open market upstream drivers, I feel like FPGAs are kind of more prototyping, or not even prototyping, but like custom drivers. People kind of build their thing out in the field. Field programming to get it ready.
I talked to this person, and he did say that he was leveraging the type 2 support on the kernel now, though, right? Like, so it was like an example of someone actually using it for hardware.
But was he leveraging what Dan posted, or what's because what's upstream is very minimal, so it might have just been what Dan posted originally.
Yeah. The summary is for everybody in the room, like, first mover advantage is open. If you want to come to the community with your accelerator driver, you get to define how this integrates to the CXL core. Until then, we just have like pretend patches that are guessing.
And you know what? That sums up my talk really well. So are there any other comments?
I just have a question about so figuring out use cases specific to like type 1 that, or that wouldn't require type 3. So one of them I think is probably RAS handling. So we might be talking about that later. But CXL.cache, technically, you can handle RAS events through the RAS capability structure without requiring all the mem infrastructure, right? I'm not talking about through the mailbox. So right now, the current infrastructure, I think, we rely on all the memory, parts of it. So is there any plans or thoughts to at least bring that piece out into the core so that any CXL entity could leverage it?
So this is also kind of aligned with the work that Jonathan started. I think Jonathan's patches to refactor the CCI stuff out of the core is going. There's other people that are going. So the word MMPT was mentioned. You talk about RAS. I know OCP has this RAS API thing. So I think it's going to be people that want to all use this core, and so it needs to become a library.
To that, looking at the current patch set, I think that more separation might be warranted, because I think like this one fix that I'm looking at that's upstream, but only really breaks when you have an accelerator device, which is our test device. I feel like the split needs to be like done now so that we're a little bit cleaner in the core, but it's not strictly necessary because nobody's using that code path. So yeah, I see where you're going.
I mean, you brought up, I think you meant, was it MCTP or?
MMPT. MMPT. Something. Like the M is a T with a P.
Okay. I see. And is that's in band still?
Yes.
And that's covering the CXL RAS capability, or is it built on top of it?
It's more closely related to the mailbox.
Well, so I guess this is what I'm trying to drive at. So if we're focusing on the mailbox and what's in the devices or the switches or whatever, but we're still neglecting the CXL RAS capability that's not part of the mailbox. So things that capture the protocol errors. So I think that is still important, probably more so for the hardware vendors and for the host, developers. And there's a lot of people that still want to do that stuff in band and OS first. We could say firmware ways to do it, but a lot of folks don't always want to do that.
I'll move on, but take a look at the work that AMD landed recently. That was plumbing a lot of the protocol error support with some core support. Right now, it is tied to that memory device, but I think it's that gives a pathway to support directly supporting it other places.
Yeah, I'm going to actually defer the rest of my time to DCD so we can get started on that. This is basically what we have. And I'd rather spend the time talking about that because it seems like we have a lot more interest in that.
I just had a comment regarding the type 2 stuff. Would it make sense to try to push more for backend validation, considering that it's for type 2 and type 3?
Yes, I think so. But again, I think we're going to need some use case for it.
Yeah, what I would love to have is somebody saying that they're going to put back and validate in a generic type 3 device, because right now we have this called CXL CPU cache and validate, which is terrible. And it uses the write back and validate instruction, but everybody hates. I would love if any kind of type 3 side operation that invalidates, like I could just, if I change the decoder, I can hit a button on the decoder and it uses back and validate. So that's my wish list item. So I hope that would be the path to get HCMDB into the kernel is to piggyback on what type 3 needs for it.
That's in the category of watch this space.
So Jonathan, we're going to have you kick this off. All right.
Okay. Oh, you're going up there.
Just an introduction. Me again. So my role in this talk, incidentally, is actually really just to give a very brief introduction and introduce the two people who've been really working on the topic from a kernel point of view, who are Ira and Navneet, who hopefully we've got them both online.
Hey, Jonathan.
Hey,
hello.
Ira's just been speaking, so we're good to go. Okay, so the agenda for this particular talk is pretty straightforward. We're going to have an introduction, which I'll get through nice and quickly. Then we're going to move on to some questions around asynchronous add and release of memory. Partial extents have raised some corner cases. Interleaving, always a challenge. Forced release was asked earlier about QEMU side of things. This is obviously what do we do about it from a kernel side of things. Yeah, some stuff on interactions as well. Yeah, apparently we're not going to crash. That's what they're saying in the room. Yeah. Option 1, crash. So what are we actually after in this talk? We first of all want to highlight some of the challenges that have been brought via the dynamic capacity feature. We want to identify some use cases because some of these questions are driven by what people actually want to do with it. And while those of us involved can conjecture wildly, we obviously represent only a small corner of the industry and people may have other use cases. Yep, and then the aim really is to get lots and lots of discussion going. So this slide can be covered really, really quickly because frankly, we already had an introduction to what DCD was. But just to recap for anyone who's joined since the first session, it's a CXL 3 feature, allowing memory to be changed dynamically without any need to do substantial host system changes. Personally, I don't think you need to restart to run without DCD, but it depends on exactly what you implemented to whether you do or not. The device can have up to 8 regions. They can have different parameters and different settings. It's all about adding and releasing of extents. An extent is a complex word for a base address and a length. That's all it is. Easy way of representing a chunk of memory. The device has to maintain lists per host. As it says here, the Fabric Manager triggers the add and release operations. And helpfully, I've got a bar over the bottom one. Oh, yes. And we will come on later to the fact that from a host side of things, it's presented as DAX. And without further ado, I'm going to hand over to my co-speakers.
Hi, hello everyone. This is Navneet. I'm working with Intel. I'm going to cover some of the challenges with what we are facing in implementing the advanced DCT features. So one of them is asynchronous DCT memory release. So if there's a DCT memory release request initiated by the Fabric Manager, which will go to the CXL device, and if that memory is pinned in the host, whether it's a user pin memory or the kernel pin memory, right? So that memory can't be released immediately, but CXL 3.0 specification allows to asynchronously release the memory, right? So what is user pin memory? If the complete extent or some part of the extent, if host is not able to release the memory, then it is in use. And once memory is free, then it should be returned back to the device asynchronously. And whether a device is, whether the host is using this memory or not, that is based on the use of the device DAX mapping, right? On the kernel pin memory side, if some of the kernel components or the device driver has mapped this memory, then this memory can't be released back to the device, right? And once this mapping is done, is released, then this memory should be released back to the CXL device, and which is very unlikely to happen. Can you help to go to next slide, please?
Sorry. Sorry about this.
Okay, thank you.
Questions?
Yeah. So previous slide. Previous
slide. Yep.
Yeah. So about this asynchronous release. So if the release is triggered by an event, so this means we will not send a response to the device until the extent is really released, right? Will this block all the event in a process in the event log on the device?
So CXL 3.0 allows, there's an option whether to give the response back to the device with a 0 extent, or a host can avoid sending the response back to the device.
So in short, you've got to respond reasonably quickly, but you don't necessarily have to release the memory, but you can release it later anyway. So you can take the thing off the event log.
So basically, we can respond with 0 extents, and later we just release it when we don't need to use it.
We will have lost the information to know that the device asked for it back should the host crash. But that's not critical anyway. You can always ask again. Right, Ari, you were saying?
I was just going to say that the event is processed, and then if the memory's in use, the actual release response is sent once the memory is not used anymore. So.
Okay. Next is the partial.
Yeah, so the one thing I was going to say about that is, though, something was already in the contract to get the memory assigned to the host in the first place. That whatever that communication path is can also make sure that the memory is offline before the FM sends the event. Like I feel like by the time the event comes in, that's too late. Like in order to keep the kernel, the simplest is the kernel just says no. If you haven't offlined it and it comes in, to say no. We're not going to play these games of partially releasing things and walking page like tables and so just trying to put that out there, like, hey, please don't build your FM with this idea that you can just ask the kernel to give things back, because the kernel just might say no to everything.
I'll add that was one of the things we wanted industry feedback on. Yeah. If there are reasons for this, and I agree with Dan, we couldn't think of any. But if there are, it is something that can be supported, and patches are always welcome.
Well, but Dan, you also mentioned partial extents, which we're on that slide now, which is a little bit different than asking for the whole. Jonathan, you said it very well that extent is a very overloaded term because there's the memory range that was originally given to the host, and then there's the potential of a sub extent or a sub range of that being asked back. And there's going to be, based on our discussion on Discord, and Fan agreed that we're going to simplify this, and none of this sub extent game is going to get played right away. And if that needs to be played, then it's going to make things much more complicated, and we need a strong use case for it. So anyway, go ahead, Navneet. I didn't mean to steal this, but this slide is timely.
Okay, so also CXL 3.0 spec allows to use the partial extents. It means that extent can be divided into sub extent, and it can be partial extent can be released back to the device, or device can accept some part of extent, right? So let's say if somebody has asked for X amount of memory, but a host can select or accept some part of that memory, then it's allowed to do that. But as of now, we are looking for any strong use case in Linux, and if there's one, then that will help us to support this implementation. Next slide, please. Next comes the DCD interleaving challenges.
Hang on a second, I've got a question.
Just more, just trying to understand the problem there. So I don't know if this is a real use case yet, but let's say a device recognizes some issue within a sub-region of an extent, and it wants to do some sort of maintenance on it. Would that be a good use case for it to request back just that piece from the host, do some sort of repair, and allow it back? It may not be an urgent thing because that'd probably be covered with more urgent events, but does that make sense? Maybe it's something that might come.
Yeah,
that would, but would it be better for somebody to flag that and have the the host software that's using the memory also flag that through the FM and tear down the usage of that memory? Right?
Yeah, right.
Because right now, I think the idea is that any extent that's handed to the host, that you're going to have a user space app mapping that entire extent, that we're not going to map huge extents that aren't going to be used just in case we want to take some back. And so if there's anybody on the host has that mapped, then the kernel has to assume it's being used, whether it's actually being used or not.
I flex that a little bit. We haven't got far yet into the virtualization use cases, but just because it's a nice big memory mapped file in the host doesn't mean that we don't have visibility of how it's mapped up into a VM.
Well, we may have the visibility, but well, okay, sure. I mean, in that case, the kernels cannot. You're right. The kernel can react without any assumptions, but still, it's anticipated that that's going to be used, or whoever asked for it probably wants to use it.
We kind of have crossed this bridge a little bit with PMEM, where with the DAX device, you can map it in gigabyte mappings, and it will never be broken up. And so if you get one cache line within your 1 gig is gone, the entire 1 gig is gone. And I mean, that's easiest because like we keep everything together. But if we need to talk about splitting, we can. Like a lot of these things are on the table. It's just kind of waiting for that one end user that's like, I really need that. I'm like, okay. But until then, we're like, no, let's keep it simple.
So on to something simple. Next slide.
Shall I move on to next slide? On the DCD interleaving challenges?
Yep.
Okay. So the major challenge here is with the CXL memory device driver that extents are coming from multiple CXL devices which are participating in the interleaving, right? And the CXL memory device driver has to keep track of all the extents, and when all the extents are received. In that case, it has to compose, it has to translate all the DPAs to the HPA and compose a HPA range, and then pass on that extent to the user space, right? So in case of the extent add, once the interleaving set is complete, after receiving the last extent from the interleaving memory device, then its device driver will construct the HPA range, and it will surface the extent to the user space. And in case of the extent remove, the very first release extent, which we receive one of the CXL device, which is part of that interleaving set, that will lead to removable of the interleaving memory. That complete memory range will be removed from the host. CXL 3.0 also allows to forcefully remove the dynamic capacity memory. In this case, if memory is pinned for a very long time, then a device can raise a forced dynamic capacity release request, and it will not wait for the host to respond back, but it will simply remove that memory from the host, right? And in that case, if any access happens from the host side, then the kernel will lead to the poison, or it may crash, right? So there's a first ignored by the Linux software, like dev error, rate limit. We can limit the error logs. That extent is leaked, and probably we will require the host to reboot to come out of this situation.
Questions coming in?
So this sounds like a very similar use case to like the error isolation, memory error isolation. So, I mean, as these kind of problems are solved and they're overlapping with some other things, I mean, are they being taken into account, or are they being treated like very independent features?
Yeah, I have, you raised memory error isolation. That's in 3.0. My concern with that is that you really need to have a kind of a contrived setup where memory cannot be online for memory error isolation, because you need to be able to take the entire, you need to be able to reliably and safely take the memory offline, all of it. DAX can do that because it's file back, so you can go shoot down everybody who has a inode map. There's no good way to go shoot down everybody that has online memory map. So I don't see how error isolation can work if the memory is online. And if it's offline, yeah, then we can force remove all day. But online memory, you can't, like, once you online it, you're basically opting into not ever being able to get it back for any reason. Yeah, we can go.
Well, yeah. So one subtlety here, which is what I implemented the first go round, is that force actually would allow the extent to be removed if it wasn't in use. Are we saying that that is a potential use case if it's not actually mapped anywhere? I agree with Dan. If it's mapped somewhere, that's a different, that's more like the memory error isolation. But if the memory is not actually in use, should we go ahead and allow the, should we recover the extent and not leak it?
But my understanding is the hardware is not waiting for us. Like the force removal is for like removal of last, like the expectation is the kernel's already crashed at that point. Like all your other communication mechanisms that release memory have failed. The kernel's probably dead at that point. So the kernel ever receiving a removal event in a state where it can process it, I think is 0 or low.
Anything we do here is going to be best effort. Maybe if someone has a use case.
Yeah, it's like
till then.
It's the what color do you want the battleship to go be as it's sinking kind of thing.
Okay.
Okay, and forced dynamic capacity will.
One comment regarding the forceful. I don't think that would be the case for like a CXL reset, where you do have to like wait.
If you're issuing that to a Type 3 device, something's gone horribly wrong.
Yeah, if you're issuing CXL reset, I would have hoped you've already offline the memory before you tried to do that.
Well, yeah, it has to be offline.
Okay.
Yeah.
Yeah. So I mean, if you're live enough to offline the memory, then you won't get the force anyway, because you'll be responding to whatever Like the front, you can walk in the front door. You don't need to kick down the back door.
I think we're good to carry on.
Okay. Okay, over to Ira for the sparse DAX region.
Yeah, so this slide, I'm really just trying to go over where traditional DAX regions are without DCD. And DAX regions are created. They're created on existing memory. These DAX devices are created linearly. They can map different ranges within that, but there's very limited control over where those DAX ranges are. And I wanted to kind of throw this slide up with a little picture to kind of say where we're at, such that my next slide, where I'm talking about DCD, we can start to talk a little bit more. Yeah, you going to the next slide? There we go. So with this, the current idea is that the DAX region becomes a container. So we're introducing this new concept within the kernel, and this kind of feeds into how user space may use the DCD memory ranges. And we're introducing a sparse DAX region where the DAX region is created, but there's no actual memory available inside of it. And then the DAX devices, right now, as a first cut, I'm still using a linear creation of them. So as you create DAX devices, they can use parts of each extent, and they can be packed into extents, and they'll jump over any gaps in the region and to fill into the extents. So the picture here is showing an initial DAX dev on the left that's creating a DAX range that maps part of a region extent. And then supposedly something's come along, created a DAX device that created another DAX range that filled up that first DAX region extent. And then the second DAX device that's actually existing right now, and I apologize for the photo because this first DAX device should have been a little smaller to the left, but now the second DAX device comes along and it actually fills up the second extent and it extends into a third extent. And then that other device goes away, and this third DAX device comes online and it fills into the third region extent. So you can see that we have 3 DAX devices here, but they're mapped differently into the various extents, even with a gap in the region itself between extents where they showed up, as well as a gap in the first region extent that's being unused and would potentially be filled in by a subsequent DAX device being created. And the reason that I wanted to go through this is that one of the ideas that we were floating around and was actually in the last patch set that went up that I submitted as an RFC was the idea that tags could be used for DAX devices to be created on specific regions that had specific tags. And so, one of the things I wanted to bring up with this slide is that a decent use case? I know tags were specifically created for shared memory, but those tags could be, because the tags are not specified directly for shared memory only, they could be used for various things. So if an FM wanted to create specific extents with specific tags, maybe that's where we want to go. I don't think that the next patch set is going to try to attempt to do anything. In fact, I'm gonna remove all labels or tags from the patch set but I think that going forward over the next year, I wanted to bring this up as a use case. Where do we want to go as far as how does the user get access into the extents that are surfaced to the region?
So I have a comment about that. So tags are going to be essential for sharing. And if the memory was to try to change behind a tag, that breaks sharing. So surfacing shareable memory under tags is essential.
I'll add one other thing, which is Dan was shaking his head, and he's right on this one, which is that tags actually weren't introduced for sharing. They were introduced for labeling for the purposes of applications. And sharing was a convenient reuse of some infrastructure.
Fair enough.
Oh,
But-
okay. I did not know that. Okay. Well, then, but then the use case that we're discussing here is appropriate. Then that
absolutely.
each extent. So should I have labels at least shown in sysfs for now, or I mean, how far? Because it's not too far to go to be able to create a DAX device on a particular region with a particular label. It's not very difficult to extend the patch set to that. But I was going to try to avoid that in the next release to try to get something landed upstream before we go that far.
Yeah, I mean, just talking about it, it just feels like something we want to enumerate. I don't think we need to have a dynamic allocation policy around it. Just be like, hey, here's the capacity with this tag available, and you can do with it as you wish. But otherwise, you don't need to relabel it or retag it. Or...
We might add some sanity checking because there are some rules about tags turning up later, although they only really apply to shared. So for normal capacity, you can add more capacity with the same tag at any time.
Yeah.
Whether we need to enable that.
Yeah, and
does it matter?
And also for shared, I don't think shared could touch any of this. Like I feel like shared needs its own ABI. It's a whole different security model and usage model.
Yep.
So okay, but if we export the tags for the extents, but we don't add any support, the DAX device, how will the DAX devices be created onto the particular extents?
Like, would you at least be able to see the address ranges? Yeah, we talk about it because I think people are going to want to be able to have a use case where they can at least make sure that one device is bound by one tag domain, and be able to and have a contract that says, oh, I want to add and release, or I want this container or whatever to use memory from this device by tag. Like,
so having again, extend the DAX interface to be able to assign a tag to it such that it would take memory from particular extents that are tagged that way.
But I feel like, already today, like there's already user space code that looks at the address space and knows how to do a complicated allocation policy to get the DAX device on the specific ranges they want. So they could start with that. Like we don't need to solve that problem for them. If that becomes too kludgy, then we can talk about like how to do this dynamically. But I think as long as you can see, I need this HPA range for this tag, then you can approximate the rest with user space logic.
But how about so how about synchronizing it with the user agent? Let's say some of the workload which is running on the host can say that give me the memory associated with this tag, and once that memory is surfaced on the host and it can see that the tag is associated with this, so workload can start using that memory specifically for the elasticity case, right? So that it can use that memory, and once it is done, it can release it back.
Yeah, but yeah, this is where we kind of need like the orchestrator people and the device people to kind of show up and say like, yeah, this is what we want to build together. Because right now I feel like we're in this talking about what we could possibly do without really knowing what people actually want to do in practice.
As I understand it, can we push the whole thing to be a user space problem from the point of view of doing the matching of the address ranges?
Yeah, like right now, like Oracle way back in the day, a couple of years ago, added this ability to look at the memory map and do the custom allocation. And people have done things like, oh, let's solve the noisy neighbor problem in user space, and they just it's an ugly bash script to toggle the DAX APIs, but you can get there.
Okay, so someone else's problem.
We can say someone else's problem until somebody screams, I think.
Okay, but we at least need the tags for the extent surface so that people know which tags are.
I think, the bare minimum. Yeah, we need to be able to enumerate that. Yeah.
Yep.
And we probably need to have more information. We need to have the extent starting DPA as well, the offset, so that they can figure that out, because that's not surfaced yet. It is
Yeah.
indirectly, but it needs to be explicit, I think. Okay. All right.
Moving on.
Yeah, so just in review, we've got, the kernel, the RFC v3 is coming soon. Based on the recent discussions on Discord, I'm going to have to do the patch set a little bit. Not that anything is particularly hard with creating regions before accepting extents, but the patch set itself was built up in a different order. So in order to get the patch set clean, it's going to have to be reworked. So look for that coming soon. Fan, I believe you've got, actually, I think this is your latest posting. I'm not sure. Does somebody have
The
a
Git
question?
tree is a bit dated. Yeah, the top one's the latest. The Git tree needs an update.
Okay. Your tree.
Yeah, it's a couple of weeks behind.
Okay.
I'll do that
So-
after the conference. But
Well, so pay attention to the mailing list and Discord.
Discord has been mentioned a few times on this in this session. This Discord is by word of mouth. But if anybody's currently a member of it, feel free to share an invite link to it. Or if you're not on it and you want to get just contact me or anybody else on it. Yeah, feel free to share the link. I just feel like by word of mouth keeps some of the keeps it sane. So yeah, but it's not it's not a secret club. Anybody, but it is.
And it's not sane.
Yeah, but if you're a plumber, then you're part of the cool kids.
Cool. So we've got maybe 3 minutes, 2 minutes left. Any more questions on this topic? We can go to coffee early. Okay. Thanks all.
All right. Thank you.
Thank you.
So we have an offset of 10 minutes with the break. We'll be back at 4:20. So
I know. Well, because the running joke is when I'm in the US, I can't bring my work laptop, so I can look on Raw, but I haven't. It's like I'm having 2 weeks off. Yeah. No, absolutely fair. I mean, the bit that worries me is the MCTP stuff is utterly different because the MCTP stack is a network socket, and you've got to address programming and a whole load of complexity. And I don't think we can merge them, so I think it's got to be a user space problem to deal with that mess. So to a certain extent, I don't actually care what the kernel interface looks like. They'll use whatever we give them.
Right, but it's just like, what am I merging?
You're merging raw commands. It's kind of minimal enabling. To be fair, I don't care about merging switch CCI. All I want to do is merge the refactor. So the split, I don't care about the driver because that's tiny to maintain and bring forward.
I know because like when they talk to me like, oh, we want to use, I'm like, oh yeah, look at Jonathan stuff. He's kind of hard to actually yeah. So but this is where you're talking about.
Well, the res API I was talking about was the conference space one, the old one, the very simple, not the mailbox stuff, not the events. Just there's a tiny bit of RAS stuff for protocol errors. Yeah. If you want the rest, absolutely. If you want to do events infrastructure, No, I'm vaguely aware it exists, but that's about as far as I go.
Okay, so they'll set it on top of MMTP anyway, or PT, or I should look up what that acronym is. Mailbox something something. Yeah. I mean, if they're layering it on top of that, yeah, it is for about a month. I hope it got it. No, I checked the other day. Yeah, it is. But it was last month, so it surfaced very quickly actually. Yeah.
Okay. Yeah, but I do agree that like the register in the mailboxes needs to be so modular.
Yeah. Well, it's one of those things. I don't think I split it enough because I think we're going to need to split it more for the PCI side of things than currently. The question is it worth an intermediate step, or do we have to wait for them to show up to do next bit? All I don't want to do is have to rebase that bloody pack set again. That's all I care about. It's horrendous. It takes me a day every time.
But in terms of like you being able to test things, you're okay with small bit
Yeah, I mean the key thing is I agree the user space interface that we present up could be anything, depends on what they actually need for their BNC use cases. But the majority of that's nothing to do with that. It's just the ripping out the infrastructure and then wrapping it with a PCI device. What's presented above, I don't think we'd ever have a problem leaving the raw commands, OCTL stuff in place. The reality is it taints, so no one will want to use it.
Yeah, would you be opposed to moving to testing?
No, as long as the rework is there.
Yeah, we were going there. There's never other reason for this.
Yeah,
the actual testing will be.
Yeah, you build it out tree, go out the main tree. Yeah, that's fine. I mean, I suspect we'll get some pushback on that purely from the build infrastructure folk who really hate things until testing that are real.
Yeah. But that's my thing. Like,
but are we bothered by an interface that taints? Well, I mean, this is a bit of the given that the interface is presented today taints the kernel whenever you use it. Is that ever going to be a problem for us as a backwards compatibility?
No.
We were always, that's like the ultimate. This may go away at any time.
I mean, so for me, it's more just like the upstream commit is like, we're merging this really for testing and maintenance and
wherever is fine.
Yeah, it's less about like I can utility it, but I agree with it. It's more like how do I include
it? No, that's fair. If we get the factory now, throw the driver wherever, we can move it later. Or frankly, just don't merge it and keep it out tree for now.
So yeah, but definitely, but I want to refactor.
We just need those boundaries to remain stable. That's all.
Yeah.
And the same will be true for the PCI stuff. At some point, I should just hack the PCI stuff on top and check it works. Should do. I mean, the only thing is they've dropped a bunch of stuff that's in CXL. So the PCI one is more limited. It's not hugely dropped. There's just some timeouts and stuff that are just not there. So we just need to be careful we don't use them. I hope so. They're horrible. No, they can't be because they're doing firmware update through it. Well, I suppose they could be. They could have some command structure layered on top that does the same thing.
Yeah, but
I don't know. I was supposed to read it. And I
was helping somebody earlier.
Well, the discussion the other way around, so the CXL spec changes are under discussion to align, because there's a few places.
Okay.
So they want to get the duplication out so that the mailbox is only defined in one place. So that was last week on some discussions.
Okay. The internal stuff before that was like just don't regress.
Should be fine.
And also like don't force people to have to switch to the new way. The new way there. You can maybe define new features the new way and define the old way. You can have migration, but don't regress the old stuff.
The only bit that may cause us grief is once we've factored it out, there will be multiple instances on the device. We just need to be careful that we haven't made the infrastructure fail horribly if the second one turns up.
Right, yeah.
But the description will be different, so there'll be one field different to say that it's obeying the standard. So they should be fine.
That was the other thing is if a driver decides to switch to the new way, then everything's available. It's not like you have to
No. It's got to be one. You can cut over. Yeah. Well, they abused one of the fields that was reserved in CXL, and if that's still set to 0 at CXL, if it's set to anything else, it's the PCR. So it's pretty easy, but we do need to actually check that. Yeah. I think we're okay because they use a different. The descriptive structure to tell you where it is different, so we won't accidentally read it. But we probably do want to smooth over the corners now. I'm amazed how fast it emerged. It was like a discussion that turned up a month later.
I'm also amazed that like this mailbox never went out. Like this mailbox.
Yeah, I'm sure it is. I'm sure I checked this the other day. Okay.
But this mailbox originally came from email.
Did it?
And like of all the mailboxes that I would pick, like I would pick any email box. Like any one of the
MMPT on the website. So what does it stand for? MMIO something. Grab my phone. Management message pass-through via MMIO mailbox. So the MMIO and mailbox were both removed from the acronym, and it just got management message pass-through. Well, that's terrible. So whoever came up with the acronym was. Oh.
I have a what is the industry? What are the devices? Particularly on what devices? So they make a generic IP. CXL QEMU, and so basically any vendor that was a card that would buy this controller, plug in your DIMMs, and go to market. I believe Sam. I don't know. Does Samsung have their own controller, or are you using their I was assuming that was like if you're building your own, I would really I don't know what they're doing. Well, also with these movies, but we do. So you see some what are we going? We have CXL. We're going to transition from default to and I know but it shouldn't be so I agree. It'll look like CXL on the front end. Just always more post so that's why I say oh no, like the solution. It's just like if I'm doing maps, then you get your number page level behind it. Yeah, I think it's very interesting that one of the panel sketches I was on, one of the Jordan Chin talked about they define type 1, type 2, type 3. Like I think they define it in terms of people are going to build type 1, type 2, type 3 first, like that's the order, and type 1 is first. So anything going backwards. I think we'll probably see type 2 right the whole point of having take up that cache. So we do this some way, but you can skip the background.
Well, this was all the resources we found out that all the CXL single algorithm and then they and then I know we technical reached out support all of them.
Okay, this is what I did. Just literally, maybe we don't. I don't care, but as long as it covers what's really there. Yeah.
But I don't it's like, I didn't know what we were saying. So you must not get a system for that. Why this time? I'm going to say that's what we need to do. People are doing this shit.
So something to note. Conference, I think, was recent. Yeah, they just announced this. So I don't want to do it again. Well, it's like a weekend. Have to is a
some people really fucking.
well, no, I mean, it's a good point. Depends on how much. Which is the 5% implementation? I look, this is real cool. Oh yeah, this is one of the favorite things. It's like everyone agrees that this exists. No one agrees on YouTube. It's awesome. Well, I'm at this. I'm at this because all the rest of the life is at see. They're like, they want to be the ones. No, I'd rather go over this. You guys go do the flash. Your device can give you 32. You're leaving the table. Just with movement. It's probably even better. I'm not sure, but just kind of each CXL card is the total number gets bigger each series. I think the calculated depending on the platform. Anywhere from 8 to 12.
Sit in the front row and pop them on.
That's a good theoretical. The function is like 60 depending on the platform. You guys are already seeing 10% 4 cards each. You're getting close to the maximum expected, which is exactly, which is like, yeah, it's nothing, right? So you would actually. Let's say it's
10 more minutes. That's what I was talking about.
Same thing with one in theory, you get 64 gigabytes a second. You do the math, but in reality, you're probably going to get like 4. And so when you do the math, here's why multiply that by 4 and 160 versus 100, it's about 2 to 1. So you want about 2 to 1. Because the way hardware works, which is probably per lane as opposed to per device. Yeah, channel. And they call it CXL set of lanes each channel. That's where it's weird. They need bandwidth more because they're not getting that perfect distribution.
There's no way I can say without
Yeah, and you have the ability to make some connections. So, but this is whatever you do, whatever you this side. Yeah, I 100% there's going to be a use case for us. I would say do it and then find that. Do it and general use case.
Yeah, it's horrendous.
It sounds like each of them
then they run into a migration thing, and it changes the work because that was dead easy, really, because you could just copy one box and it copies. But now,
yeah, straight up like it's pretty
Like this is fine. It's the case where you've got a double offshore, then don't want to pay
somebody that's a good idea. We added this and then they all steal one. It's got to be added.
So the question becomes,
You never see use cases. This is how So you can't change one task you set. Oh, so I chose not to implement it in CPU sets for that reason. I didn't want to and then so yes, obviously, why did you do this? Why did you do this? And then secret. This is not secret. Run out of memory. So it's not a constraint. It's not. Basically, if I have 300 gigabytes of I start so because you're available bandwidth. So you're still going to get moderate. So really, this weighted interleaving is most useful. There's a lower down, there's an upper down. There's this sweet spot. Where you get this big performance boost and then it kind of turns off. And so one of the living right to get that extra 10 to 15% on top of the yeah. One of the reasons
have you seen bombs
so if some things are giving it and some things aren't. One guy is losing and choosing to be the best. What is the effect of the system-wide?
Oh, 3 minutes. Yeah. Oh, no. I see. Oh, yeah, I write that. Is there resistance?
Have you heard about the kids doing with like trying to do unit testing for CXL kernel
What's that?
code? Unit testing for.
Yes.
Okay, you already.
Not as such. You just mentioned it earlier. That's how I heard about it. You said you must talk to Jim.
Okay, yeah. So he already explained the.
Yeah. Usual unit testing. Yeah, I saw your feedback on that. Some of that region code is irritatingly hard to work out what it's supposed to do with the spec. So writing the unit test is a challenge. There's some evil stuff in there.
Like build these like just in some basic
Yeah, for the topology stuff, yeah.
And then validate all the bare cases stuff on that too.
Hello, hello. All right. Okay, so this is the adding RAS support for CXL port devices. And this presentation was put together by Robert Richter, my coworker, and myself. Robert was not able to attend today, so here I am presenting. All right, so CXL and RAS. As we all know, CXL can support 3 different protocols. That would be CXL.io, CXL.mem, and CXL.cache. And as you can see here, we have a table from the CXL spec, and it shows the different RAS requirements for each protocol. In general, it's analogous to the PCI protocol errors. And so protocol errors detected by CXL components are escalated and reported to the host through PCI errors. And they're using, the CXL.io protocol. And specifically, they use uncorrectable and correctable internal AER errors. The delivery is actually using messages over CXL.io. And the RAS protocol errors are handled differently than the device errors. Device errors are actually using the event log in the mailbox, and it uses a totally different interrupt. And so that's not covered here, and we don't want to get those confused. So we have the PCIe port bus driver. It's used to bind to port devices, specifically bridge class ID. And in the in the probe routine, the driver actually filters out for root ports, event collectors, upstream ports, and downstream ports. And if it isn't one of these subtypes, then it returns an error. The PCI port bus probe routine then actually reads the capabilities of that device, and it's looking for services that it can support. And this includes the AER, the power management event, the hot plug, and the virtual channel. And so the bus driver actually includes service drivers for each one of these services, if you will. And I also wanted to point out that the AER service driver itself is not usable unless you have your BIOS set up for a native AER platform. or OS first handling. And also, the kernel must be built or compiled with PCIe AER config option. So this brings us to the AER error handling flow. Once the device detects a protocol error, it actually delivers a message to the root port, as we mentioned earlier. The root port actually saves off the bus device function of the error device, and it writes it to the AER error source register. The root port then notifies the OS through the AER interrupt, and so we have the AER port service driver that is bound to that interrupt, and it handles the interrupt, if you will, and it reads the AER source ID, and it extracts the BDF, the bus device function. And that's the information, if you will, for the error device. And then the AER port service driver, first thing it'll do is log the AER error, and then it'll call the callbacks if they're registered for that device. And that could be for correctable or uncorrectable errors. And then finally, that service driver, if it's necessary in the case of a fatal error, it can quiesce the device, or it could do a logical disconnect as well. So we have a recent upstream from Robert Richter and myself, and it addressed the CXL 1.1 downstream port error handling. And this was necessary because the RCH CXL 1.1 mode uses a downstream port implemented as a root complex register block. We call it an RCRB, right? The RCRB doesn't have a bus device function, and that's what causes the requirement for this patch set. The PCIe spec defines the RCRB without a bus device function, and that's not going to actually work with the AER port driver because of what we discussed earlier. The AER port service driver expects a real PCI device. So as a result, the AER flow is a bit different, right? The detection in the downstream port is the same. It sends the notification to the RCEC, and the next thing that happens, though, is the RCEC's bus device function is written to the AER source ID. Now, it doesn't quite make sense because it's the RCEC BDF. It's not the error device, because the error device does not have a bus device function. And so what happens next is the AER service driver recognizes this special case. It has a RCEC BDF, it has internal errors, and it's a CXL device type. And in this case, the AER port driver, from the changes in this patch set, it'll actually parse the RCIEP. That's the children endpoint of the event collector, and then it'll actually call the error handler for that to handle this case. And so I should note that this patch needs to be, I'm sorry, the patch was actually accepted. It's in 6.7. Okay, so this brings us to 2.0, also known as VH mode. And what I mentioned about CXL 1.1 does not apply here because it's a different topology. And so this is looking forward into the future with what needs to be done. And so we have some constraints that we'd like to consider. First of all, we would like to maintain the PCIe bus driver and the service drivers. And the reason is that we need this other functionality. For instance, we need hot plug. We need the virtual channel. We need the power management events. And so we don't want to get rid of that. And the second consideration or constraint is that internal errors are device specific. Yes.
So is Bjorn here? Bjorn Helgas? No, in person. Yeah, because I don't know, but Bjorn has talked about not liking the PCIe port service driver and wanting to get away from that model. I haven't seen a proposal for how to get away from it, but like that's just there's some danger there, and I feel like CXL is going to make this break one way or the other? Like, really going to say grin and bear it and keep it, or somebody's got to bite the bullet and
Right.
refactor the stuff?
Yeah, John had mentioned this as well. It would probably be one of the options, but it's a much heavier lift. And it's significant because it touches everything and more invasively, if you will.
Beyond did accept a performance monitoring driver that had a similar requirement, doing a fairly hacky solution to it very recently, purely on the basis that he didn't want to delay that for ages.
Okay.
So it may be a case of an intermediate solution and then come around again later.
Okay. So this may be something we want to revisit with the option or solution you're talking about then. Okay. We'll keep that in mind. Thank you. I'll go through and discuss what we found. We had 3 options with the understanding that we want to consider this. So we also want to look at our requirements. The first is scalability. AER is not a CXL protocol. It's actually a PCIe AIR protocol. And so we don't want to limit ourselves with whatever we implement. We don't want it to be CXL specific necessarily. Also, we need to remember that these are reported using internal errors, correctable and uncorrectable internal errors. And as far as handling goes, we also need the handlers to be able to implement logic specific to that technology or device, and which gives us the flexibility to handle that specific need. And finally, we have enablement. We need the driver to be able to be enabled or disabled on a per device basis. So our first solution was to add a CXL RAS port service. We actually created a proof of concept, and so we were able to begin some of the testing. So what we started with was adding the CXL service driver next to the other service drivers. So, it was, if you will, parallel with AER, the hot plug power management, and the virtual channel. We modified the probe routine to actually look for a CXL DVSEC capability, and if it was present, then you know you have a CXL port device. So the first challenge that we ran into is that there was a lot of required code for mapping, for discovering and mapping the RAS register block. And so we were faced with, do we export this from the existing CXL driver or do we copy it over? So we didn't want to,
go ahead.
So we didn't want to add or increase coupling between a CXL driver and the PCIe bus driver. So we copied it over, and it got deeper and deeper and deeper. And we were going to have to do the same thing for the logging as well, right? There's already logging in the CXL driver, and how are we going to handle that? We would have the same problem with this new CXL RAS service driver. So quickly found this wasn't the best solution. Not only that, it doesn't meet all the requirements. This is just addressing CXL devices, right? And we said that one of our requirements is that we would like for it to work for all PCIe devices. So we moved on to solution 2. Solution 2 was to actually update the existing AER service driver. What we did is we added an internal error callback. This is for the correctable and uncorrectable errors. And we added it to the existing struct AER RPC. And this actually added the generic callback functionality for the port devices, but it wasn't for PCIe devices, right? We actually limited ourselves when we put it into the AER RPC structure. It was an improvement in that it didn't add as much code. It reused the logic from the AER service driver, but again, it was just port specific, not PCIe specific. So we learned a little bit more, and then we looked at solution 3. It's a variation of 2, and it allows any PCIe device to take advantage of the internal error callbacks. And what we did is we moved the callbacks away from the AER RPC struct, and we actually put it into the PCI driver error handler. And so this is where all the correctable, uncorrectable callbacks are. So again, yeah, we put that in there. And so we also had to add a registration function. It's important to note that in order to assign this, it has to be done at runtime, because remember, you're actually a PCIe port bus driver. And so when you're predefining using the macros for your PCIe device type, you don't necessarily know what kind of, if it's a CXL card or not. So this is one caveat. It's not great, but it's better than option 1 and 2 issues. And so for this example, you would have a CXL port device. It's still bound to the PCIe bus port as it is done today, right? But you would have the internal error handlers that you could actually register such that you would get your logging for your port device error handling. So what we have here is a comparison for solutions 3 and 2. Solution 2 was limited to port devices, which doesn't, again, meet all the requirements. Solution 3 was actually supporting all PCIe devices, which we found met all the requirements. So that is it. It's a quick presentation. Discussion, feedback, Q&A.
Was there any other consumers on the PCIe side of the AER, like handlers? You know, the CXL you showed it, but is there any other ones inside of the kernel right now?
No, right now,
okay.
AER for the most part is consumed by the AER service driver.
Okay.
And in fact, you'll find very little AER logic outside of that.
Okay.
And this was something that we ran into in our patch set, if you will.
Okay.
It's not totally true. It's true that the actual handling of the AER is at that level, but there are a bunch of callbacks on correctable errors that are still.
This is true. And if you look at the parameter that's passed, it's not AER related. And so, and we had to change the exporting of the data.
Yeah, you had to add extra on
in our patch set for that, because there was actually a delineation that AER was not exported logically or available in drivers themselves. And in fact, I don't know if you remember, there was a patch set that went through review, and that was one of the changes.
Yeah, sure. But it's not true that AER errors don't end up processed by drivers. They just do it at a lower level after you've done some interpretation of what was going on and issued.
Yeah, and the callback is, the callback handler is invoked as well.
Yeah.
And it allows the driver to do some processing. Yeah.
Is there any, it's a bit of a dodgy route, but is there any possibility that you could use a child device of the PCI port and basically search for whoever knows to handle the error to avoid, I mean, at the moment you're trying to set a callback sort of one layer up in the tree, and that feels a little strange, but I wonder if it's possible to basically go look for a handler in the device model. You don't want to search everything, but if you could search children, I can't remember if the thing is a child.
So the root port children?
Well, it would be the root port or switch port. Yes. I'm not sure. I'm not sure what it looks like in the device model at the moment.
So are you asking, when the AER handler runs, how does it handle the children devices?
No, not so much. Sorry. Not so much that, but whether there was a path that would avoid you. So at the moment, from the description, if I understood it correctly, you're basically going in and replacing a handler in the PCI port driver.
Well, we're actually introducing a new internal error handler.
But you're writing it from a lower level.
A registration function.
Yeah, it sort of feels like it's almost going the wrong way up the device model. Maybe I'm interpreting it wrong, but that was sort of where I was going. And the question was whether you could go find in the right direction.
So I guess the question is during registration, like how do you know when to register the callback? So maybe that's something we.
The callback is in the PCI port driver.
No, it's in the device driver. Whichever one binds to the device.
The endpoint?
Yeah, whatever, the endpoint or anything that. Yeah.
So how does it work for a switch port? There's nothing bound to it.
So this is a question that I think is open.
Oh.
And basically, because all entities in the topology, at least for CXL, right, they have CXL RAS capability. I think it's a requirement, right? So we need something to bind to them to do this. I think the simplest method maybe that Terry was explaining is if they have a driver, then we can add handlers to them. And so whenever the AER handler walks the topology, like let's say you say on a special case like this, you walk the topology, and if it's an internal error, now you call this special callback for internal errors that's specific to that device. This might be something that could be broken out from the CXL core, something that I was asking about earlier, where at least this part could be common, and any sort of CXL entity could have this loaded.
Yeah. I think we're definitely going to get to the point where, like, I think register discovery and probably mailboxes are going to be broken out so that anybody can use them as a library. So if that changes your calculus on solution one, like, that's what I was raising my hand to say, like, oh yeah, I think we should break that stuff out and make it a library because you don't have to duplicate it in all over the place.
That was a consideration as well, but it seseemed like a large change.
It's a large change, but I think we have to do it.
Okay.
Like, I think there's enough people that are interested in, like, oh, we'll just copy, like, we just copy the way CXL does it is a refrain I've heard.
Another option to consider is that the current PCI capability functions, again, rely on PCI config space mapped registers. And if it could somehow work on MMIO, it would shrink a lot of the logic in order to find the register blocks.
But have you thought about how this interacts with, like, CXL port objects? And I know we talked about, oh, maybe we could put something in but that kind of has the same problem as the PCI port driver. But in these error handlers, like, because error handlers are mostly just reporting which link had which problem.
Right.
Like, do you think you're going to want to report, like, the CXL port object name in those reports, or is it just going to, or you only care about this BDF had this event, and it also happened to have this CXL RAS capability attached to it too, and let other people figure out, oh, this BDF means this CXL port.
No, I think you should be able to provide the port information as well.
Yeah, but yeah, I feel like that's crossing, like, port, like, driver boundaries, like your generic PCIe error handler driver doesn't know anything about this CXL port topology thing on the side.
It also, there's another question as well, is when do you do the registration, which Yazid mentioned. We don't have CXL port PCI discovery, right? So we would have to choose where to do that. One place you could do it is in the port discovery and underneath the ACPI enumeration, right? When that happens.
Yeah. Part of how we ended up with the CXL ports kind of on the side was so we didn't have to bother anybody, and, like, we could just kind of build this topology and all these rules. But, like, this makes me wonder, like, if we need to reverse that and actually go be PCI core integrated.
That's what John and I were talking about this morning. Yeah, because right now we don't have any CXL port PCI devices.
Yeah, we have a lot of PCI problems to solve to do that, because there is no way of having a driver other than the PCI port driver for downstream ports. That needs re-architecting for a whole bunch of other reasons around performance monitoring and other standards that are expanding PCI on that only apply to ports. But it's a big job. We're going to be a while before we get there. Yeah, you could do that.
Jonathan, I think you had a good point though on looking at top down from the port once you have the AER error, and then possibly from there searching. And there's actually merit in that because of scalability, and that you could actually find the right device, if you will. Because otherwise we actually have, this is probably an issue with the design that something that would have to be resolved, is that right now we're talking about a callback per port, right?
Like, I mean, building on Jonathan's idea of like broadcasting these things, like, I mean, it's already, the recovery is already kind of a broadcast to the topology, like, hey, somebody downstream of me handle this. I mean, like, would it be terrible to say, I'm going to broadcast this all the way to the, I guess you don't want to have to depend on the endpoint driver being there to say, oh, endpoint, do you have any ports up, all the way down? You got to stop at the thing that caused the error.
Let's take this offline.
Okay.
All right, thank you.
Thank you.
I know the child of the
Page up and page down work.
Oh, okay.
Page up and page down are what works? Okay. Hi, everybody. John Groves from Micron. And this is a little more of a proposal for how we need to do things down the road with CXL3. I've been spending a lot of time thinking about how to make shared FAM, fabric attached memory, work in a way that gets us some leverage and it doesn't end up like 3D Crosspoint where it's hard to use and it doesn't get used. That's yeah, I know, for sure. Yeah, it is missed by a handful of people. So I thought about calling this Meet the New Abstractions, same as the old abstractions, because that's kind of the approach I'm trying to take. So my goals in talking about this are to raise awareness of fabric attached memory capabilities, to point out the need for a shared scale-out FSDAX file system, which I'm going to try to convince you is important. And then to start a dialogue about the architecture, and I'll describe a prototype we have. I've got some ideas about the architecture, but I'm not of the impression that these ideas are going to survive all the way through. So real quick, a lot of what we've been talking about is what I would call pooling. That's where some memory gets given to a host, it gets onlined, and a lot of interesting work being done there around tiering and stuff like that. But with sharing, it's not going to be onlined in most cases, I claim. Onlined memory gets zeroed. If you're sharing, it's not a case where you want to zero it because you probably connect into it to find contents in there. And oh, by the way, that's a lot like persistent memory, right? So, and actually, can anybody confirm whether the 3.1 spec got released? No, okay. There's a handful of things that can be talked about. It was going to come out today, then it's tomorrow. I'm sorry. Okay.
Surprise, everyone.
Yeah. It's, yeah. There is one someday. Okay.
That may be it.
Yeah, I know. Now that I did that, it might not. Okay. So CXL shareable memory looks like tags capacity. There will be a way, if you know the tag, to find the DAX device. And so you could imagine putting data sets on raw tagged capacity, i.e. raw DAX devices, and apps could open it. But I claim, and I've got some backup info on this, that's not going to be good enough. There's a world full of apps that know how to open data sets in files. And we should let them do that. Because if we do that, we get a ton of leverage. If we don't do it, then there's a world full of apps that need to be modified. So what does it look like? The CXL devices are DCDs. Well, this is hard to read on this screen. The DCDs are effectively devices with an allocator built in. And so, but what gets allocated is tagged capacity. There are cases where it's not tagged, but it doesn't make sense to do that if it's shareable, because you need to agree on which one's which. So that's enough about that. Some observations about shareable memory. It's doesn't make sense to online it. It's going to be zeroed, you know. The most accessible use cases are things that already know how to deal with data sets and files. It's PMEM-like, I've already said that. Cache coherency, you have some options. There's a hardware-supported cache coherency mode, but the laws of physics apply. That's going to be expensive. I don't think, my opinion, it's going to be attractive for some things, but software managed or cases where you're reading and not writing are going to be really interesting because they don't have any problems with the cost of the coherency. And real quick about FSDAX, this kind of unfolded over the past few months as an epiphany for me. The VFS layer already lets you have a file that maps to some special purpose memory. And that's kind of what you'd like for shareable FAM. The only problem is that the way that existing FSDAX file systems are implemented, they have write-back metadata, and that's just something you can't mount in more than one place. Although technically, you can mount it read-only from more than one place, but that's hacky. But so if a file has the SDAX flag on it, and if it's paired with a DAX device that has the right functionality, then if I mmap it, I'm doing exactly what I hoped I would be doing, which is I'm doing cache line level accesses to the DAX memory, which in this case, the interesting thing is if it's shared. So can we enable it for a lot of use cases? There's the column on the right is kind of the data science and AI tool chain, you know, Jupyter and Pandas and NumPy and Apache Arrow and et cetera, et cetera. These things share a lot of infrastructure for dealing with data sets and files. And in fact, they've done some things that are really helpful for fabric attached memory for reasons that are actually a little different from the reasons we care about them. Apache Arrow, for example, is what the data science community, the developers of that, they call it a zero copy format. And the idea is that you wrangle your data all the way to where your columns are vectorized in memory, you know, packed like a C array, so that vector instructions will run on it and computation is efficient. By the way, that's how you'd like your data that you're going to share in FAM to be laid out, particularly if you've got SDAX files pointing to it, so you mmap it and you're just really accessing it. And so, let's see, in these kinds of data sets, read-only data is common actually too. And again, can we make this ecosystem deal with raw DAX? Yeah, one app at a time we could. But if we have a file system that can give you access to it, then we'll get them all. Now, it's still a subset of those use cases that are interesting, especially the ones where the data is actually packed in memory the way you'd want it. Question, Dan?
Are any of those using like multiple processors, at least on the same host, like doing a map shared of the same file?
Yes. Yeah. And we've run experiments. I don't have data to share about this, but we've got a good set of sort of plausibility arguments around. It's like, take Apache Ray. That's effectively it's an orchestrator. It's an orchestrator for your AI or computational data science kind of workloads, which I'm not up here as an expert on, but I'm observing them and learning about it. It's really typical that you start with a big data set and then you shard it up and kick off 250 processes to each work on a piece of it. A really interesting use case, and one that I believe isn't difficult to demonstrate the value of, is start with that big data set in shared FAM as a zero copy data frame. Then each of the sub jobs will run a query against that data set to get the subset it's supposed to use. That's already part of what Ray does. And actually, we're showing a demo at Supercomputing this week where the value of not having to move the data around actually overcomes the fact that the CXL memory is slow right now. And so, because what would you want to do with FAM? Well, you'd want to have like more FAM than you can fit in a server. You know, when I was in school as a physics major, we used to say computationally there's two kinds of problems, the ones that fit in memory and the ones that don't. And that's still true. There's a lot more memory, and at Micron we're in favor of that. But but if you've got data sets that are really huge, even if you're sharding up the computation on them, it can be it potentially is a real win to put them in FAM where you've got more of it than you can fit in a server. And then in some cases, you can run computation directly against that. Yeah, it's probably slower, both in terms of performance and latency, but you can fit things you couldn't. But also, you can have it there for querying out what you want to do the individual workers work on. And in some cases, those will be moved into DRAM for that. So I think I'm going to try not to say a whole lot more about these use cases. Okay, so this is really just about why not DAX? Why won't DAX just enable us for a lot of apps by itself? So I'll leave that unaddressed. But the slides are online, and I'm absolutely happy to talk to anybody who wants to discuss it. So existing FSDAX file systems, the way, so I've studied this stuff because we have a prototype. I'm going to talk about that in a minute. But they do write back metadata. The metadata is mixed into the memory with the data. And so that's just not multiple mountable. They also do some things that I think can be avoided here, allocate on write. You know, the prototype we've got is pre-allocate. So the procedure is special for creating a file. Once a file is created, the procedure for using it can be exactly the same as using any file. You know, extra points for doing it via mmap because that's really doing the thing you want to enable here. But also, and then there's some constraints like truncate's a problem. Right. Didn't Linus once years ago say we lost the key to the clue box on a list talking about truncate? I'm pretty sure he did. Okay, so the current implementations just can't scale out. So here's what I think the requirements are. It needs to be an FSDAX abstraction that lives on top of tag capacity. Files have to efficiently handle VMA faults. That's like the kind of the main thing file systems do, right? The system says, where's the page at this offset in this file? Because there was a page table miss following a TLB miss. And so that's got to be handled fast. And then, yeah, we're exposing memory. We want it to be at memory speeds. We have to distribute metadata in a shareable way. That's something that addresses something that isn't done that way in the current DAX file system, because they were put there for a different reason. They were put there effectively to subdivide NVDIMMs, PMEM. And finally, it has to tolerate clients with a stale copy of metadata. And so somebody might think of more requirements. I want to hear from you. So what do we have right now? Well, started with a RAMFS clone, added an ioctl to the files to say, okay, here's the extent list of DAX extents that back you. Here's how big you are. And then that gets set up, and the SDAX flag gets set on the file. At that point, the VFS layer knows what to do with that file, provided the interactions between the file system and DAX work. And right now they work the same way they do in XFS, and there's a couple of issues there, but I'll get to those in a minute. There's a log format. Right now it's implemented as a append-only log structured file system, so files can be allocated. You can dump data sets into it. There's a master who gets to actually append the log and do the allocations. There are clients who consume the log and make notice from time to time that it got appended. And so, you know, when you play the log, it instantiates all the files. There's an interesting little twist to this because the metadata is local to each client. Metadata does not get written back to the log. I claim to enable a bunch of apps that already know how to share data. That's actually fine. But it's a thing that should be discussed and debated. Log play for the current prototype is handled from user space. I think that can continue to be true. User space just reads the log, instantiates the files, calls the ioctl to set up the allocation. Like I said before, files are allocated by the master. And this is interesting. Data may be writable by clients. At the log play time, at each client, the file can be made writable or not. And so this actually, if the software knows how to deal with one writer, multiple readers, or multiple writers even, you can do that. You can also have the files be read-only for everybody but the master, that kind of thing. So, and there's this, there's a CLI that gives you the ability to allocate a file. It gives you the ability to copy existing files into it, pre-allocate, put the data there. And I claim this is actually sufficient to enable a lot of stuff. And I don't have demo data right now, but we're playing with it. I hope to be releasing RFC kind of patch sets pretty soon. So, looking at how it works, MakeFS is master only. Playing the log, the master might remount the file system and need to play the log as clients would. Creating a file, you allocate some capacity, create a local file backed by that space. That's actually create the file, then make the ioctl call to turn it into a SDAX file. Initialize the data, put the data in, and then commit a log entry. And so then I'm waving my hands. I'm not really talking about how we distribute the log right now, but assuming that we can do this and this is eminently, I claim it's already working, then anybody who's watching log for appends gets visibility of the files that got put in there. And the policy for what they're writing, whether they can write it, doesn't have to be the same for every client either. And then usage, POSIX read and write work because that works with DAX. It just looks like a mem copy. And mmap works. And that's the thing you're really interested in. So let's see, there is one more problem, and that is the PMEM versus DAX thing. Right now, if it's persistent memory, it gets a block dev PMEM device. That device supports this IO map API such that the VMA faults, I believe they go to the DAX device, but the DAX device knows to ask the file system, so the file system gets asked translate this offset in a file to an offset on a DAX device. And then the DAX device finishes up by figuring out what address that is or what struct page and reports it back. But character DAX devices don't have a fully working IO map subsystem. So right now what we're doing is we're telling the system they're block DAX devices. Go ahead, sorry.
The PMEM devices.
Right, yeah, sorry. Yeah, we're telling the system they're PMEM devices. And that's fine as a workaround for that issue. I'm assuming that the RFCs that we put out for this, we'll just have to solve that problem. I'm sure I'll bug you, Dan, about it. But so anyway, so back to goals and plans. And I'm kind of amazed that I've gotten this far in this time. Probably everybody's like, what the hell are you talking about? But I believe this is an opportunity to enable a ton of stuff. Really a lot of stuff gets enabled by this. And again, the data science tool chain, they already figured out that so a couple words about that. What does the workflow look like? Well, there's probably some comma delimited data that you're starting with, some data set from somewhere. So you start reading that stuff into a data frame. It's actually not entirely uncommon for like one line of Python code slinging data frames to double the memory usage of the app at a given moment, because they don't know how much they need to allocate. So they start taking it in and then they allocate some more. So that's why, and in these workflows, you already interact with your data at a data frames and files level. So there's already this workflow where you convert it into a zero copy data frame. That packs it. And the users of these workflows are already doing this kind of stuff. So that's what you want to do and put it into FAM. You don't want to put your comma delimited data in FAM because it's inefficient use of space. And like I say, hope to start posting RFCs and finding out who hates it and who loves it. And question, Yazin?
Yeah, have you thought about the error handling flow here? Like the hardware industry has been trying to take the surface area of memory errors and contain them smaller and smaller, so we don't like have catastrophic events, right?
Right.
But here we're gonna have like a big file system that's shared across multiple hosts. I mean, if we have one memory error, how does it affect everybody? Does everything go down? Does just a set of jobs get killed? Can we, like, maybe we can give more thought to that?
Yeah, so that's an area that I can't do real justice to right now. I mean, whoever read poison and machine checked is down, right? But another thing about these, I don't think they're super long lived in general. It's like you're going to massage up some data, dump a set of data frames into this thing. Clients are going to mount it. They're going to do something. But I believe in some contained amount of time, they finish and you unmount it. Like there's no way to delete these files right now. You could, well, I can let you truncate it shorter or delete it if I don't reclaim the space, because what I can't guarantee, at least without doing a lot of work, is that all the clients know I deleted something. So space that's been allocated to something can't be reclaimed without addressing that issue. But that's, so errors, I don't think it's unique to this. I mean.
Yeah, I think maybe you make a good point. If it's constrained to short-lived work, maybe it's like, you go hard, you go fast, you take a lot of risk for the performance benefit.
Danger is my business.
You live dangerously. But if the job only runs for a little while, that's
right.
Okay. So maybe it's not worth the return to figure that out.
Well, I mean, I think it'll ride the coattails of whatever figures out that stuff too, because
sorry, is what you have so far predicated on the existence of back and validate, or are you claiming to do, like, for example, you have the single writer, many reader? Is the intent to just instantiate the entire device and then just do a giant flush to make sure it's coherent? Or
so it's, I believe this is orthogonal to cache coherency protocols. When you're appending the log, you're going to have to do write back and validate and things like that. Whoever's appending the log has to use locking to serialize both allocation and log append. what the client applications do needs to make sense. So the easiest thing to say makes sense is the master dumps some files into there, make sure the cache is written back. Everything's software coherency, but the clients are all reading.
Okay.
So then you're good. If they're writing, I mean, you know, a comment about the laws of physics. Cache coherency among multiple threads or processes on one machine is already expensive enough that we try really hard to avoid that. And that terminates at the processor cache. With fabric attached memory, whatever you do has got to go all the way out to the memory. That's going to be more expensive. That convinces me that the killer app for this is probably not there. But it's important to be able to do that. But yeah.
So you're claiming, just to be clear, you're claiming this could be useful even on top of existing 2.0 infrastructure rather than having to wait all the way for 3.0 with some level of
well, sharing 2.0 really doesn't do shared memory, does it?
Doesn't really do, but
we have some of that. Right.
Quote
so
unquote.
If you've got shared memory, you can do this. Okay. Absolutely. Thanks, everybody.
Thank you.
Hello, everyone. My name is Ravikiran Gumaluri. I work for Micron Technology as a system architect for CXL Group. Today, we are going to talk about CXL memory tiering for heterogeneous computing. Along with me, my colleague John Gross will also talk about various kernel patches that we are pushing and how important it is for CXL 2.0 adoption. So I'll start quickly on the agenda topic. I'll not be touching all the slide contents. I'll try to keep more focused on the kernel patches and solutions, what we are looking help from Linux community. We'll talk about memory demand and scaling challenges. We know the industry has this challenge, what CXL memory expansion is going to solve with these problems. Specifically, I'll talk about hardware-based interleaving policies that today we have, which is solving the bandwidth expansion use cases. But we feel strongly that software-based interleaving will solve, and it is more flexible. That's where the Linux kernel patches, RFCs, which are under review, is very important for us to get into mainline. We'll talk about how we are enabling the software interleaving, and we'll talk about next steps and call for action. I'll quickly go through the memory problem here. We all know the memory demand in data center applications, it is growing 26% year over year, and the memory capacity is not doubling. So there is a huge gap between the demand and the memory scaling. The processor speed is actually increasing with every 2 years, and memory latencies are improving only 1.1 times the memory wall problem, and you can see huge gap between CPU performance and memory performance. The third one is basically talking about the capacity per core. It's not really scaling, as you see the graph there. So there is a lot of demand in bandwidth and capacity requirements, which the current systems are not able to scale. How CXL is going to solve it, that we'll see in the next slide. CXL memory expansion gives you additional capacity when you attach it to the CXL system. There is a no-brainer there. You are adding more capacity to the system, and it can be achieved in various ways. This memory can be exposed to the application transparent way, where applications are not aware of this memory models, and OS is managing, or user space libraries are managing an app that is transparent way. And applications are also aware of this number of memory topologies, and they can use libnuma if application is aware of those topologies. And applications can also be modified with libmem-kind in order to utilize these new CXL memory nodes. In a CXL switch gives us flexibility of scaling more number of CXL nodes that can have additional capacity to the system. So capacity expansion is a no-brainer. You are attaching more capacity to the system. Now, coming to the CXL memory bandwidth expansion, today we have multiple solutions to solve bandwidth expansion, especially the hardware-based interleaving is the easiest way to deploy. The software interleaving is also there in our Linux kernel with interleaving between various tiers today, but they have some limitations. That's where we are trying to propose. There are a lot of RFCs that work need to be done as soon as possible for CXL 2.0. We'll talk about each individual CXL bandwidth use cases today, how we are using today, what are the background, what are the drawbacks of it, and how software interleaving is solving those problems. So this is one of the way that today the CXL 2.0 is getting adopted for bandwidth expansion use cases, where the system address space is interleaved between local DRAM and the CXL memory. An example is if you have a 12-channel DDR on the host and you have 4 CXL cards, the system address map is chunked into 16 chunks, and then you are distributing complete system address map with these 16 chunks. The process is it is easy way to configure in your BIOS configuration. You just configure it, that's it, it will work. But the problem is kernel is not managing the memory allocations here. It affects the kernel memory. It hides NUMA topology. It's a flat memory model, basically. It is a fixed configuration, and it will not be applied for applicable for all the workloads. So it's a constraint there. And one of the other requirements for this is the CMM module has to be ISO capacity towards the DRAMs. Meaning, if you have 64 DIMMs, 64 GB DIMMs or 96 GB DIMMs, even though your CXL memory is 256 gigabit memory, it has to be ISO capacity. So you're not really utilizing the higher capacity of CXL memory here. So those are the existing challenges today. The kernel is not able to really involve here. We are adding additional bandwidth to the system. We have lots of limitations here. On the other side, we have also utilized the existing software interleaving model, but we have tuned that to in a way between hardware and software to extract better performance out of it. Here we are trying to do, instead of 12 DRAM channels on the CXL on the host, looking like a 1 NUMA node, we are trying to split a NUMA node per socket. We are splitting that into 4 NUMA sockets per node, so that we get 4 NUMAs on the given local node instead of 1 CXL node. And CXL node is seen as another NUMA node. So basically, we are splitting. If you are not doing this hardware configuration in BIOS to split the 12 channels into 4 NUMA nodes, you will be left with 1 NUMA node on the local and 1 NUMA node on the CXL, where you will be interleaving between 1:1 configuration. So with this configuration, we are trying to have more number of NUMA nodes on the local, and CXL is 4:1 ratio. This is one of the sweet spot we saw with this configuration, that we are extracting maximum bandwidth out of the system. So the process, it is NUMA topology is enabled, kernel is able to manage the memory allocations, overcomes the capacity limitations imposed by hardware interleave in the previous slide. The cons is it has fixed configuration again, because once the BIOS configures this as 4 NUMA nodes, you cannot change it. And with each workload, you have to tune normally these ratios, and you cannot really change those ratios with this kind of configuration. The next one was a software heterogeneous interleave. Today, the kernel, if you see, you have 2 tiers, and if you want to interleave between those 2 today, it just asks you what nodes needs to be part of interleaving, but it doesn't talk about weightages of each interleaving. Earlier, what we did is, in given NUMA node, local NUMA node, we split that into 4. So we are able to play with the ratios of 4:1. In this, software is giving actually a flexibility that each node is now you're giving a weightage. So instead of splitting the hardware into 4:1, I can achieve same kind of configuration here with 80 pages on the local and 20 pages on, which is 4:1 kind of ratio with simple software interleave. Today, the kernel doesn't support the weighted interleave. What is our proposal is there are various methods for supporting weighted interleave, which is benefiting for the system, overall system bandwidth improvement. So those are things that we are looking. My colleague John Gross will talk about various patch set that has went into the kernel patches which are under review, and we would like to have a discussion around that. Thank you.
Yes, so I'm a software guy who works at a hardware company, and yeah, who's with me? And so, you know, I don't know, starting maybe even 2 years ago, it was pointed out correctly that a balanced interleave with regular DDR and CXL memory would help for bandwidth constrained applications. For latency constrained applications, that's a whole different ballgame. But So being a hardware company, they were all interested, and I know some other hardware companies that are interested in this too, in having the BIOS menu configure balanced interleaves. And I don't speak for anybody, but I feel certain this is going to be available. But what really makes sense is to do it in software at the allocate pages for lazy VMAs level, because if we do that, then we don't affect the kernel, which if the BIOS sets it up, it's going to affect the kernel too, unless they think ahead and fix that somehow. And it's not going to affect applications that you don't want to apply the policy to. And so that's a thing that we really think that as a community we should address. Yes, Yazin. Got the mic.
I just wanted to ask maybe for clarification. So when you say interleave here, do you mean like actually interleaving the physical memory, or you're leaving them separate NUMA nodes and you're doing, just like you said, the allocator is just choosing?
So what I'm saying is the get free page call that happens when an address gets touched that hasn't been allocated yet for a VMA, we should apply weights then.
Okay.
And there's a sequence of patches that actually, I guess this is the slide for that. They've changed a little bit. So there was Meta put out a patch. Johannes, is he in here? I saw him earlier today. Johannes Wiener submitted it as an RFC like June of last year. It just took 2 NUMA nodes, but you could apply a weight for the 2. And if you set the mem policy to interleave before that patch, and still today, because that patch isn't in, you just get 1-to-1 across whatever nodes you wanted to interleave across. With that one, you could set a weight. That was well received, but Anish was working on the mem tier support. Big details about that are out of scope here, but mem tiers are groups of NUMA nodes. And so I reached out to Johannes a few months ago, and he said, well, we're not working on that now, but why don't you pick it up? I started looking at it, but then I was talking to Greg and some of the developers at Micron, and Greg picked it up and ran with it. But we've been through some iterations. V1 was mem tier based because that's what we thought the community wanted. So that means weights for mem tiers. Each mem tier is a collection of NUMA nodes, 1 or more. And so, but the feedback was that didn't look right. And feel free to start chiming in if you want to, Greg. So V2 is NUMA node based. And I think one of the questions for the community at large is, what are mem tiers for if not this? It seems like they're for something a little different. And I don't think I understand the answer to that completely. But it doesn't particularly matter to me which it is. And my understanding was that mem tiers made sense if you expected to have an accumulation of NUMA nodes that were really similar. So then that kind of aggregates those. If we're not expecting that, then I'm not sure tiers apply here. And then V3 is C group based, which I love because it's hierarchical and you don't have to have just one set of weights for the whole system. But there's an ongoing discussion on the list right now, and there's some pushback from the maintainer who would have been affected by it. I think.
V3 was actually memory control group based, and there's actually a V0 that was based on mem policies. So there's actually 5 implementations.
Thank you, sir.
Do you think hardware interleave only makes sense on sub-page granularity?
Well, so there's hardware interleave and there's heterogeneous interleave.
Mm-hmm.
So we're talking about heterogeneous interleave where your DDR is interleaved with CXL memory, and that's fraught with some stuff.
Yeah, my point is though, like, so software can do something at the like page level, like whatever the memory management unit can address, right? Like at that point, it doesn't really matter. But I think sub-page is that you hope you can light up more channels, right, with a smaller granularity, right?
Yeah, don't do that. Because if you do everything at page-based in the page tables, your TLB pressure is going to kill you.
because you really don't want to route them. You want nice, big, huge pages for the simple case.
Right.
In this particular case, perhaps not.
So yeah, with the software interleave at the allocate pages for VMAs level, I don't know why I especially care that it's page granularity or even huge page granularity.
So you're saying, I guess that's is that a problem there? Like if you want to interleave across NUMA nodes, page granularity, you're going to have a problem there, right? Because like you have to, the fault will never be contiguous, right? There's no way around that.
Today, probably, there's nothing stopping you deciding that you're going to do it at, say, 2 meg level.
Okay.
Other than working out how on earth to configure it. But I mean, theoretically, it works just as well if your data sets are way bigger than 2 meg anyway.
Yeah. So
yeah, traditionally hardware interleave was always sub-page granularity though, right? Like for DDR. Yeah. Weird.
I've seen it be larger than that when I worked for a server vendor, but typically it is. So moving on, I mean, you know, the Robbie might want to talk to the particular details of this data, but the net is that if you get the balance right, you know, we've got tests that show 35–40% performance improvement on purely bandwidth constrained applications. And clearly that, you know, if I've got this is made up numbers, 3 gigasecond of DRAM, regular DRAM, DDR bandwidth, and 1 gigasecond of CXL, then the right ratio is 3:1 as a starting point, and then see whether the data matches that. And that should give you a third additional bandwidth in terms of napkin arithmetic. And what we're trying to do, why we're in favor of this patch set, is 2 reasons. Whatever, it's going to evolve a little more, but 2 reasons. One, we want to enable the ability to do this aggregated bandwidth thing. And 2, we want to talk people out of doing it in hardware where it's going to affect apps that don't benefit from that. And so, yeah. And this is short-term, you know, CXL2 kind of stuff. And do we have, oops, I think I skipped something. Oh yeah, just acknowledging the people that worked on it. Did I miss another one? Oh yeah, so in the presentation, which is up on the Plumber site, there are links to the patch sets that have gone so far. You know, and we would ask anybody who agrees with us that this is good to help us promote it.
So I was wondering about, oh no, I've lost it. Come back to me in a second.
Okay.
I have a question about your results.
Yes.
So you had the 6 CXL devices. Can you share the CPU server like platform, like the server that you were using and the form factors? Or I'm just curious about the 6 devices on there. Yeah. What
so we cannot share the platform.
Okay.
Of the other reasons.
Okay.
Certain people in this room will.
Intel's the on platform.
Okay. Yeah, you know, for reference, I was thinking of the OCP where it was like 4 CXL devices on the super micro server, but that was publicly displayed, right? Yeah. So that's why I was kind of curious. Right?
The front end is the Siemens one.
Okay. Okay.
You can plug in few more on the back
More. Okay. Okay. Thank you.
This goes back to Tajan's comments on the MC group is how do we determine the minimum viable product for this node interleaving? Like the fact that I don't know. You talk to Johannes, like why Johannes stopped, because he was somebody who could talk to the application side,
right?
Because like there's a lot of stuff we could do here, but it's not clear like what we have to do and what is the front use case that some application managers like, we need this in the kernel because we need to distribute it. And
right. Well, so Greg and I were talking to Johannes about this earlier, but not trying to close the sale, right? It's my understanding that he works at the same company as one of the C group maintainers who doesn't like it currently, but he just doesn't know it well enough yet. That's what I'm thinking. So there's a discussion to be had there. I really
so there's a big world outside of C groups. If if the weighted interleaving kind of thing works only not only for C groups, but also like for NUMA nodes, that would be transparent to everyone. C groups may or may not be used.
Well, so you're right about that, and Greg has something to add. But what I like about C groups is, given the hierarchy, I can override the weightings for some applications, and that's kind of beautiful, right? I mean, I certainly don't know that that one set of weightings will be good for all, but I do know that, at least one set of weightings as opposed to 1 to 1 to 1. There's a huge thing.
I'll add one thing to that and then I'll pass. There's two features really. There's the control of who gets the interleaving and who gets the weights, and then there is the attribute of the weight itself. And I don't think those two things necessarily have to be co-located, but that's kind of the debate as to where do these things belong at the moment. It feels like weights should be more node, and the control should be more mem policy or C groups, and it's just a matter of figuring out who's willing to take the maintenance cost.
Right.
Yeah, I mean, I guess my ask is, what's the ask for, let's say, the hardware vendors? So you're saying like maybe doing all the interleaving in hardware is not the best approach here. So does that mean we kind of go back to some of the earlier ideas of just having the topology, NUMA nodes, everything just very clearly describe the hardware as it is, giving proper weights, and then leave everything to the software and
so
keep the hardware basically simpler?
Yeah, well, so I'm not trying to talk the hardware vendors out of doing this. I know of unnamed industry companies who want it. So they can have it. It's just that CXL is not going to look good all the time if that's all you got. And CXL will look better if it's got something flexible. And one set of weights for a system, so that, because you still opt in with the interleave policy, that's a mem policy, right? So if the mem policy for interleave is set and there's one set of weights, that's pretty good. And that's probably MVP. If we could get it into C groups, then there's a hierarchy and you could override it, and some things could have a different policy than others. That sounds better. We might find out in practice you never need to do that. I don't know, right?
So with the hardware interleaving set, we have analyzed multiple workloads. It's suiting to 1 or 2 use cases, but not scaling for all, especially if you have a capacity sensitive applications and bandwidth sensitive, it's not scaling for capacity. So this software interleave gives us flexibility. If you want a bandwidth expansion to bandwidth sensitive application, you use interleave. If you don't want, you don't use it. That kind of flexibility we have. But the hardware interleaving is forcing us to have a specific configuration, not scaling for most of the applications.
Right. And something's going to behave weird in the kernel too, by the way.
Just for a comparison point, on traditional many socket systems, there's always a BIOS option to interleave across all of the DDR channels in the whole system. No one ever turns it on. A few applications do. Yeah, okay.
Some people do turn it on.
Okay. A few people have. Yeah. It's hard to implement. Yeah.
Right. Yeah. Some things are just to show you why they're a bad idea. But anyway, yeah. So I call you to action to help us get to the right solution that can get in and get it in.
How many more?
Oh, infinity.
But like what are you willing to, if you had to ruthlessly pick the minimum thing you wanted to build, like would it be global system weights like 80-20 kind of, would that be the first thing you would build? Or
it would be configurable one global set of weights, I think. Configurable though. Settable.
The weights would live with the nodes, but the control would live with this the mem policy, with the mem policy capable of overriding.
But what if there's weights with zero control? Would that be a viable product at all?
Are they set stupidly or well?
I mean, yeah, they're set statically.
Right.
Control in this case just means mem policy interleave. So control in this case really just means you have some ability to opt in, right? In this case, it's M-pole interleave. You set for your task, and then it is inherited by all the subtasks. To what extent you expand that control to be able to turn it on or off or change the weights, that's a different question. That's why I said a single global node base, like the weight becomes an attribute of the node, and then mem policy eats that as input, is probably sufficient as an MVP, with the optional control extension of being able to override those weights using mem policy. And so mem policy having, you know, an optional weights array, for example. And that is basically the combination between two patch sets that have already been put up. But barring the ability to get the weights into a global setting, just having mem policy with the optional weights is probably sufficient to prove the point. And then if you want to apply it more globally, you could either expand it into C groups or node, I suppose.
I'm basically trying to play the role of Tajan and his comfort level, and yeah, and so like if you get, it feels like if a control is like on or off, and then there's a static policy on the platform, that's not great, but it's like it's progress, right?
Right, and it's as flexible as if the hardware did it.
Yeah,
right,
and that's
just not very flexible, but actually more so because you still don't have to apply it to everything. Yeah.
Yeah, and that's why I said throughout the entire thing, it's always an opt-in policy, which is, you know, I'll say probably the best of all worlds, because it doesn't affect anyone unless they want it to. So.
Have we got enough information to set the weights? Because one of the classic things when HMAT was added is that we only advertise nearest, so nearest initiator to a given memory. And I worry a little that that's obscuring half the data you need.
Yeah.
Well,
to jump after this, but so part of the node version of the patch set was to touch on the accessors. Like, what if I have a task on node 0 and it's accessing weights across a socket, and that's very complicated. And I think we've all determined that's probably too much for an MVP, and probably we need to think on that problem a little bit more.
And an assumption that that a balance that seemed obvious would be the best balance isn't necessarily valid either. I mean, for a given workload, you might play with the balance in order to figure out what worked well. Hey, thank you, everybody.
Oh,
we're
is this
all
yours?
at the end.
Oh,
Yeah.
Brilliant.
Weird.
We weren't able to do that last year.
All right. Speaking of bad ideas, this is hopefully a little comedic relief, but this topic is actually chock full of bad ideas. So hopefully, if you don't leave this talk with having cocked your head to the side and going, I don't know about that, at least once, I haven't done my job. So the thesis of this talk is very simply, what if move pages but for physical addresses? And that should make you cock your head to the side from the beginning. So the thesis here is, so I've talked to just about every CXL hardware vendor that has either talked about their hardware openly or not, and they're all kind of discussing, all right, if we implement multiple levels of memory in our device, what kind of fun things can we offload? You know, if a simple idea might be, if I have DRAM and NAND in the same device, maybe I can offload page faults. Whether or not that's a valid idea, not for this talk. All we have to think about is, in terms of memory tiering, there are real problems there. And the core problem is, if you do that, all of a sudden, a lot of your monitoring features go away. For example, and we'll talk about this a little bit, transparent page placement uses page faults to detect what's hot, what's not, and what to demote and what to promote. So a lot of these vendors start to talk about, well, what if we offload the ability to track heat maps or idle bits or hotness lists? What can I provide tiering software in terms of telemetry to make it easier? The problem is, as I alluded to, Devices only talk host physical address, or at best, and at worst, device physical address, which means any data you get from these devices is going to be in that format. And that's a problem because there isn't really a way to utilize that directly. You have to convert that right now back to a virtual address and a PID, and use either the sysmove pages system call or some of the internal kernel interfaces. So, you know, I kind of allude to this. Why do we even want to do this? The current state of tiering, it's kind of chunked into 4 or 5 different mechanisms right now, and they're all kind of eaten by a handful of systems like Daemon. But I kind of chunk it into 4 basic ones. Interception-based, which is, we call it kind of legacy Optane stuff, where you have to replace allocators and things like that and be able to detect access. IBS and PEBs are sampling-based systems. They can be configured to provide either virtual address or physical address, which is kind of interesting from a security perspective. Transparent page placement uses faults and some level of charging to do demotion and promotion. And then basically page or folio flag monitoring. Simple one is the idle bitmap, for example. All of these have some performance implications that I want to touch on very quickly. So IBS and PEBs, for example, the most common thing that people are using right now to determine hotness of data is basically LLC or last level cache misses, right? And they configure it to give them, using libperf or some other interface, combination of virtual addresses and a PID. And they utilize that with move pages or some of the kernel internal interfaces to actually demote or promote pages. The problems with this, and there have been a number of talks in the past couple of years on this, prefetch traffic can actually bypass these sampling interfaces, which is problematic because the prefetcher can drive like 66% of all bandwidth. So are you really being accurate with what is hot and what's not? There can be some runtime overhead based on the sampling rate. That should be obvious. There's no free lunch. But more generally, these PMU counters are actually already being used in a lot of cases in a lot of these data centers, right? So they may not be available in the first place, or if they are available, you're potentially time slicing them. So yeah, transparent page placement. This is rather new. Primary mechanism here is fault-based. It basically marks some pages not present, detects if they get accessed. If they don't, they get marked for demotion in some cases. And some recent extensions enable hot pages on lower tiers of memory to do promotion. That's actually what the memory tier component in MM does right now. So there's some, the additional extensions. So the problem here is fault overhead, right? There's tail latencies. Every time you add these faults into the system, you're going to eat the cost of that fault. And it can be complicated to tune depending on the workload. So it's not a one size. It tries to be a one size fits all mechanism, and it's decent in certain areas. But if you're trying to figure out exactly, you know, how my software should be utilizing the memory, it's hard to configure sometimes. Idle bit tracking. There is a mechanism in the kernel to do some level of page bit tracking, and the kernel does mark some of these PFNs as idle or not idle, and so you can determine what has most recently been used or what has not been used. Userland can actually set these idle and not idle bits directly if it wants, in order to tell the kernel's reclaim feature, hey, don't push this out to swap, etc. There's some problems with this too. From userland, at least right now, last time I looked, there's this mass migration from struct page to struct folio, and that broke a lot of flag stuff from userland. So looking at some of those things may not be accurate in the most recent. It depends on the interface you use, I'll say. So some of the debugging interfaces aren't quite there. So the other thing here is it's actually PFN based. So in order to use a lot of these interfaces, you already have to have the physical address anyway, which is problematic in some senses, but could be useful if you are getting this information from the devices. And so we come to the proposed stuff. So a lot of the hardware vendors I've talked to are saying, okay, I want to implement maybe a super device with DRAM and SSD and network-based CXL traffic, and we're going to do all the swaps and all this fancy stuff behind the scenes, and that's great. And maybe they even have a working prototype. And then they've come to us and they've said, okay, we have a problem. software doesn't like it when all of the memory is out in the really cold tier and we don't know how to get Linux to promote it. So how can we sweeten the pot? How can we get the hotness data out so that the kernel or some other piece of software can say, go ahead and promote this off of the device as fast as possible. And they've proposed all of the mechanisms you can imagine: idle bits, heat maps, hotness lists. I've heard them all. The big problem is physical device addressing, right? Devices have no concept of tasks whatsoever. Don't have a concept of virtual memory, so all you get out is a physical address. And the reverse lookup to go from physical address to virtual address, because there is no interface in userland, for good reason, to do this, is very, very expensive. There are a few interfaces you can cobble together to manage it. They all require admin, right? So that should be obvious. But because there's no standard interface, it's hard to build core kernel support for that. And because there's no standardized interface, especially in the CXL spec, I wouldn't imagine the core driver is going to implement anything like that. So it's all going to be vendor device specific extensions to do this, right? Yes.
You are mentioning about lack of getting not able to get the virtual address, and hence you want to do the reverse lookup, which is expensive, right? So I thought getting physical address isn't it good enough for you to actually place the page wherever you want? For example, using the kernel already does that, right? Using the interfaces that you have. The migrate interfaces works on a struct page or a physical address, right?
Yeah, so it's two things, right? So a lot of the monitoring mechanisms operate on, you're right, struct page or monitoring some of those features right now. These device vendors are talking about pushing some of those monitoring mechanisms down into, we'll take page faults, right? If the kernel is setting some of these page fault pages, or some of the, we'll say the present bits to generate these faults, it increases overhead. So some of the vendors are asking, well, what if we forego that and we handle in FPGA or Magic Hardware Land, wherever, the ability to just go out to my second tier of memory on my device and handle that page fault internally? Well, now I've gotten rid of my monitoring mechanism from the kernel's perspective or the CPU's perspective. And so you have to, if you were dependent on that to control promotion and demotion before, you have to replace that with something that the device gives you. But the core problem is the device can only tell you device physical address. And this is where the standardized interface becomes the problem, which is if you don't have something in the specification that says this is what the device shall implement if you want to do this, chances are you're going to have a bunch of random drivers implementing it. They're going to implement their own command sets. And I'm interested in a standardized interface that enables us to build a more general solution for this class of device.
Another question I had related to the IBS thing that you are describing.
Sure.
You were mentioning about the prefetch overhead. What exactly is the you mentioned that it would kind of pollute or reduce the efficiency of the sampling data that you have.
So it's not an overhead. Prefetch traffic, so the hardware prefetchers will do quite a bit in order to front run software. And IBS and PEBs in particular, I'm kind of picking on those two particular monitoring pieces. They either don't report last level cache misses for prefetch the same way, or they miss the prefetch calls entirely. So if you were to hit one of these pages or cache lines that should be marked hot, it may not actually show up in the data that you're requesting from IBS or PEB. So it's not that there's overhead. You might not have as accurate a piece of data as you want about the state of the system. Thank you. You got a question?
Regarding the standard interface and whatnot, one idea that's floated around for maybe a year since I think it first came out of LSFMM was to have some sort of like doing the promotion in the kernel, yep. Not in triggered by user space.
Yep.
Is have some sort of kpromote D where you would harvest the different ways of tracking hotness, fault hinting, performance counters, whatnot. And have that daemon kind of like K-swap D, I guess, harvest that, and then do the promotion asynchronously. That's easier said than done, but that's kind of like where the kernel MM folks are trying to go.
Yeah. And did you have something? Yeah. Oh, the only thing I was going to say was, and when we cross into what interface should the device provide, there's a little bit of a chicken and egg scenario. Until someone kicks the can over the line, no one knows what to implement. And that's kind of where I'm at in terms of, well, here's an interface you can use to prototype. Go ahead and do it. Whether or not this is ultimately the best interface, probably not, but we'll, we can discuss it.
Yeah, and also one of the nice things about that is that like you have different kinds of the inputs can be virtual addresses, can be PFNs, whatnot, and again, automatically kpromote-d would solve that.
And Daemon eats a lot of this already, so Daemon implements a lot of that abstraction as well.
You almost kind of said a solution when you're talking about how the monitoring mechanism doesn't get updated or doesn't know like that the device knows something that the kernel's currently monitoring mechanisms don't understand. But like that seems like a simple matter of hardware. Like what if hardware updated the structures that Linux cares about?
True. The hardware would have to know about those those things, so that
these would be Linux specific devices.
Yes. So there is that. Yeah.
Of all, they're probably architecture specific. These structures are not necessarily
Right.
constant cross architecture.
Well, and also they might even be built.
Get rid of the legacy ones.
So for the sake of time, I'll kind of jump through a bunch of these. So I've talked a little bit about the reverse lookup overhead. You can do this right now using userland. You can do all of this reverse lookup. There's a couple of different things, and we tested. What does it actually cost to do this? What does it cost to do this when we're running with additional compute available, and when the system is pressured for compute as well? So to kind of summarize these awful charts, the top is the chart when there's compute available. And you see as we utilize more memory, right, 64 gigabytes on the left and 512 gigabytes on the right, and the subcolumns here are number of processes running. There's basically an expected linear increase in the amount of time it takes to reverse map this amount of data. So 512 gigabytes, it takes 90 seconds to reverse map a whole memory map of that region. If you use bigger pages, it'll be less, obviously. But 512 is probably not the target figure for some of these devices. You might be looking at 8 terabytes of potential memory for really big capacity plays, right? But it gets really bad when we look at as soon as your system is pressured for compute, all of a sudden it goes from a linear increase to you got to steal those cycles from somebody, and now you're putting additional bandwidth pressure on, you're putting all this stuff in order to move that data, and you're actually eating up data in the process because you have to build this reverse map before you can make any decisions about where you want to move the data. And the thing that really shoots this dead is the fact that this is only good for one snapshot in time. So during all of that time, during that 90 seconds or 5 minutes that you're building this map, your data is going more and more and more out of date, right? And so that means it's less useful for the latency tiering perspective. So that's, yes, reverse mapping is actually really, really bad. So there is limitations to doing these offloaded tracking limits, and I'll talk a little bit more about the implementation of MoveFizz pages. Obviously, I've mentioned hardware has no contextual information about a page. So a physical page could actually be reused very rapidly between dying and created processes. And so if you migrated that page up, well, it might just stay hot, right? Because if that particular page is being used by the kernel to just reallocate between processes, well, it's going to look hot, but that's not actually realistic. Transparent huge pages actually potentially cause this problem. So by no means is this a perfect solution, but it is. I do think it is enough to start the conversation. And there are many unknowns in this scenario, as we discussed already, largely because all the hardware vendors are like, what could you implement? And the software implementers are like, well, no one does this, so I'm not going to bother exploring use cases, right?
Just a quick comment.
Sure.
The rapidly reused page is definitely hot. It may not be hot if you're trying to do your migration in a particular application, but it is something you want to keep cache hot.
So the rapidly reused page would be one in which it is hot for a very short amount of time and then is freed and released back to the system and then utilized again. But it is hot in the context of a hardware address or a physical address, not in the context of a virtual address.
Yeah.
Right.
Agreed.
So that this is where it gets a little confusing to keep straight between virtual and physical. So I do have a working implementation of Move Phys pages. It's based on version 6.6. I can't get it up to 6.7 on the main at the moment because I have to do some pretty nasty rebases. But it is actually 2 commits. It's very stupid simple. There's one refactor commit that takes the existing Move pages code and makes some of it reusable. And then the second commit implements the syscall. This is only on x86, but if you have a particular, if you want ARM, I'll do it on ARM, and it won't take me that long, probably an afternoon. And it actually just does, it reuses all of the Move pages infrastructure, and then just all it does is remove the PID from the syscall, and you hand it a physical address instead. Something to note, yes, it still does the reverse lookup anyway because it has to, right? So we are going to eat an RMAP. So I think I have it on the next slide. Per page, you still have to do this RMAP walk on the folio that the page belongs to because you have to validate that you're not going to violate C groups, CPU sets, and things like that. So you have to go check every VMA that it belongs to, check that it's actually migratable, and then move it, which you already have to do anyway in Move pages. So it's not really that crazy. There might be one locking thing that I may have violated for C groups. I got to go back and fix that. Just one small one. But it also reuses like a VMA migratable to double check that these VMAs, this page belongs to a VMA that's actually migratable. So we are validating whether or not these pages are movable in this interface. We're reutilizing the vast majority of code directly from Move pages as well. And there's already been a little bit of feedback and some other ideas. The first one I've heard was, well, can we create the interface but not the syscall? I think that's totally valid. There's 2 issues that I see with that. First is it allows development, but really only in drivers or in the core. And until you have a standardized interface that devices can implement, it doesn't necessarily, it may hurt adoption or it may hurt people that are interested in doing it but don't want to write a driver, right? May not encourage the open development. So if somebody actually figures out how to do this really well, they could just close source their driver unless we GPL this particular symbol, for example. And then the other one was the obvious feedback, which was userland shouldn't talk, physical addresses go away, and that's a legitimate concern. The feedback I would say there is that IBS and PEBs can already be configured to not just give you one or the other, but both the virtual and physical address mapping. And that's why it requires capsys admin. And that's why this interface would also require capsys admin. So from a security perspective, it's no worse than IBS and PEBs in that sense. So I think that's what I got in terms of questions. We got 3 minutes and then we can all.
I think the other concern about giving the syscall though is also like forever cutting off the core kernel from a policy mechanism. Like
yeah, no, absolutely. I totally agree with that. And that's why I said this talk is chock full of bad ideas. But it does give something for people to prototype against in the meantime until we kind of figure out whether or not this is an actual legitimate idea.
But if we imagine a world where a CXL memory expander is giving hotness coldness information, couldn't that expander driver be a generic thing that just calls internal Move pages?
And my follow-up question to you would be, would you integrate that without it being in the CXL spec as a full-formed feature? That's all I'm saying.
Yeah.
Well, no, as the kernel maintainer, it was like, wouldn't you want to see that as an actual generalized feature that is defined?
I mean, like, yeah, we generally operate on what's in the spec. Yeah.
And that's all I'm saying is I completely agree with you. And my feedback would be that sounds like something we need to standardize.
Do you think there's this, like kind of going back to David Lohr's point, right? The applications that would make sense is like, who's going to consume this, right? Like you could say like sophisticated applications wouldn't need this, right? They'll handle placement on their own. And then kind of the ones that, make the best case possible, let the kernel do it internally, right? Like, why give them this power afterwards, right? Like, what is?
Yeah, one of the pieces of feedback that I got was the kernel should do this, and as we just discussed, I actually agree with that.
Okay.
But it is a little bit of a chicken and egg scenario. I think until you can prove there's a legitimate use case,
Yes.
The kernel will not do it. Yes. And so the proposal here is, can we get something so we can at least get it moving along? And in the meantime, the patch is there; people can use it.
Yeah, that's what I was going to say.
Yeah.
Why do we need it upstream for the purposes of development? And we need the refactoring and everything.
So the
absolutely.
refactor, yes,
Yeah,
and the core interface, yes, but it's a. I don't think necessarily the syscall as it is should be upstream. I think the refactor should and interface be made available. But it's fun to talk about implementing a new syscall.
Got it. So this is for the purpose of CXL device memory, kind of hotness access tracking. Why would the user space be the first be handling this kind of information? Why wouldn't they have
It's kind of in the same realm of the discussion we were just having. Yes, ultimately, I think a general tiering piece of software is probably better handled by the kernel because it has better general information around the system. But there is a bit of a chicken and egg, right? So if we get something that allows us to do this type of movement in user space, we can very rapidly prototype off of custom devices, off of a variety of things that happen to pop up.
I see. So these devices would expose something to the user space,
Yes,
and show the hotness information.
And it would be done probably in the form of vendor-specific mailbox commands to be able to. I mean, well, no, I mean it's in the specification and it's carved out, but as a, I'm joking, but it is good as a prototyping interface. Just to be clear, I'm not saying that we should ultimately try and get it into the standards, right? We should ultimately try to do that. Yeah. Yeah. So, did you have more?
I mean, just for the record, we had a user space agent working with Intel Optane memory that was using very similar kind of syscall, but Optane is dead. So very curious what's gonna go, what's gonna happen.
Yes. Medic. No, you're right. And there's actually quite a few projects. I mean, Damon is already trying to do some of this by abstracting some of these interfaces inside the kernel as well. So there's clearly some level of want or need for this type of interface. Whether it ultimately ends up as a syscall, probably not. But again, fun to talk about in that context. That's probably it, and then we got time.
Can you think of another reason for, like, besides memory policy, that we'd want this in the, because basically think of another minimum viable product for moving pages, driver directed page moving, and then maybe we could get that piece moving upstream and solve this other problem later.
Yeah, and I think that's probably a better way to do the initial RFC is the refactor patches plus an interface, maybe from the CXL area that allows you to define some device feedback as to hotness.
We're kind of doing this with the type 2 stuff where we're just kind of like, imagine somebody who cares about this, here's some patches.
Yeah.
But yeah, it's hard to move forward with that.
Yep. Yeah, it's a chicken and egg problem, right? Until you find the use case, it's hard. We are technically over time, so this will probably be it.
Comment actually. So I'm working on a prototype and an experimental implementation somewhat related to this. I have in fact posted an RFC a few months back. This is regarding using of IBS provided hints essentially to do the page placement both in for regular for migrating pages between regular nodes, as well as for hot page promotion. So this is essentially use the physical address provided by IBS to do the movement.
Yep.
So rather than doing it from the user space, I was trying to get everything done from the kernel by using or driving the existing NUMA balancing logic, both for regular migration and hot page promotion. So I'm having a talk about it on Wednesday also. Wednesday in the referee track, I would request audience this kind of related if you find it interesting, maybe.
So maybe follow-up question: are you finding that the NUMA balancing interface is sufficient, or would it be better to have a direct interface you could call akin to move pages that just says move this set of pages in particular?
Right now, the way IBS works and the way it provides data for each access sample, NUMA balancing interface is looking pretty good for me, but it is not the only use case. There are other subsystems like Reclaim might be there, right? Or maybe Daemon itself might benefit from using these accesses. So I want to debate about all those things in the talk to see what should be that interface. Should we have a common subsystem which actually collects all this information and makes it available to the consumers within the kernel, different subsystems? But to answer to your question, for NUMA balancing, IBS works. I feel naturally the interface works.
If I'm thinking of the same thing, that's been knacked, just because you end up doing too much processing in the kernel.
Yeah. Well, that goes back to there's no free lunch. You're stealing the cycles from somewhere, right?
But I don't know over time, but like, do you really need per page thing? Could you, like, would it be enough to say like, go poke a sysfs thing that says promote this node or demote this node? Like, is it?
There is another patch set that I don't think is public yet that is aimed at that. And that is, I think, another, like, who's willing to take on the maintenance cost of it, where it's maybe not necessarily promote this node, but maybe like take 10% of what's on this node distributed randomly and move it up or down or whatever. And I think that is a very solid proposal, especially in terms of rebalancing for interleaving, for example. Now that we're in like solidly software defined memory land, you can come up with a billion use cases that might show up. The question is, as always, who actually wants it? So yes, I think there's a place for that interface for a variety of reasons. Is it, when you talk about 2-layer memory devices, potentially with DRAM and SSD, you really want to know what's hot on that to get it off as fast as possible, because the tail latencies can kill you. So that's where it may not be sufficient to just have a general interface. You may want, I really want this page off of there because it's killing me, right? Cool. Thanks.
Thank you, organizer. Yeah. Big thanks, David Lowe, for curating all those talks today. Yeah, a lot of work. Keeping us on time. Yeah, I was like, I think it should be Greg if I ever see Greg. Oh, it is Greg. There's a lot of There's a lot of I know, I feel outnumbered. Tomorrow.